Bon dia a tothom. Em complau molt donar-vos la benvinguda a la Jornada Olga Ladyzhenskaya. Aquesta jornada és un dels actes acadèmics més rellevants de la nostra facultat i avui arriba a la seva 20a edició. Enguany recuperem la presencialitat i la normalitat, quasi del tot, i això és important i ens agrada molt perquè el contacte personal és una part fonamental de la vida acadèmica i per fi el podem anar recuperant. M'acompanyen en aquesta mesa dos dels membres de la comissió organitzadora del curs Ladyzhenskaya, la professora Ángeles Carmona, el professor Albert Mas i a la meva dreta el professor José Manuel Mazón, Mazón para los amigos, que serà el primer ponent de la jornada. Vull agrair a la comissió organitzadora del curs, formada per l'Albert Mas, l'Àngeles Carmona, el Xavier Cabré, el Joan Sánchez i l'Andrés Encinas, la proposta que van fer per a matemàtica de l'any i tota la feina que han fet per tirar-la endavant fins avui. I també vull agrair la presència dels conferenciants que ens acompanyen. El professor José Manuel Mazón, de la Universitat de València, el professor Giuseppe Mingione, de la Universidad degli Studi di Parma, i la professora Stefania Cherubini, del Polytechnical de Bari. Malauradament, a última hora, la professora Cherubini ha hagut de cancel·lar el seu viatge a Barcelona, però ens farà igualment la seva xerrada per streaming. Per això abans deia que hem recuperat quasi del tot la normalitat. Thank you very much, Professors Mazón, Mingione and Cherubini, for your contribution to our Ladyzhenskaya Day. La jornada d'avui, com ja he dit, començarà amb la conferència del professor José Manuel Mazón. Després tindrà lloc el lliurament de premis del concurs Ladyzhenskaya, organitzat conjuntament per la Biblioteca de la FME i els professors de l'assignatura Història de la Matemàtica, les professores Mònica Blanco i Maria Rosa Massa. Aquí també vull agrair a elles i al personal de la biblioteca l'organització d'aquesta iniciativa. Després farem una pausa pel cafè i acabarem la jornada amb les conferències de la professora Cherubini, que com ja he dit serà per streaming, i del professor Mingione. Espero que gaudiu totes de la jornada i que en tragueu molt profit. I ara passo la paraula al professor Albert Mas, que ens presentarà la primera ponència.
Moltes gràcies. És un plaer per nosaltres tenir el José Mazón com a conferenciant d'aquesta jornada i, com ha dit el degà, primer diré unes línies sobre la seva trajectòria científica. Llavors, José Mazón és catedràtic d'anàlisi matemàtica al Departament de Matemàtiques de la Universitat de València. Es va doctorar en matemàtiques a la mateixa universitat l'any 1980, sota la direcció de Manuel Valdivia, en l'àrea d'anàlisi funcional. Des de 1990, la seva recerca s'ha centrat en l'estudi de les equacions en derivades parcials no lineals, principalment relacionades amb les equacions sorgides en diferents àrees de la ciència, com ara processament d'imatges, ciència de materials i cristal·lització, teoria de transicions de fase i problemes de difusió no lineal. Pel que fa a la seva trajectòria científica, ha estat director de 5 tesis doctorals i investigador principal de 10 projectes de recerca. És autor de més de 120 articles publicats en revistes prestigioses amb més de 2.100 cites, segons Massinet. El seu treball sobre el flux de variació total, realitzat en col·laboració amb Fuensant Andreu i Vicenç Caselles, va donar lloc a la monografia Parabolic Quasi-Linear Equations Minimizing Linear Growth Functionals, que va ser guardonada amb el Premi Ferran Sunyer i Balaguer l'any 2003. En col·laboració amb Fuensant Andreu, Julio Rossi i Julián Toledo va estudiar diferents problemes de difusió no lineals i no locals, els resultats dels quals es recullen al llibre Non-Local Diffusion Problems, publicat l'any 2010. També ha publicat en col·laboració amb Julio Rossi i José Toledo el llibre Non-Local Perimeter, Curvature and Minimal Surfaces for Measurable Sets, el 2019, i recentment, en col·laboració amb Marcos Solera i Julián Toledo, el llibre Variational and Diffusion Problems in Random Walk Spaces, el 2023. Sempre ha dedicat un gran esforç a la vessant docent de la seva carrera. Una prova d'això és que també és autor de 4 llibres sobre anàlisi matemàtica per a estudiants de grau. Un d'ells, anomenat Càlculo diferencial, teoria i problemes, és avui dia un referent imprescindible en els ensenyaments de grau de matemàtiques. Llavors, com he dit, és un plaer per nosaltres tenir-lo com a primer conferenciant d'aquesta jornada i ens farà una xerrada que es titula...
Problema de la difusión infinita en las ecuaciones de difusión. Cuando me dijeron que tenía que hablar, le pregunté a Xavi, bueno, ¿de qué querían que hablara? Y me dijo, un tema de tu investigación, pero que la audiencia es amplia, entonces tiene que entenderlo todo el mundo. Entonces pensé que uno de los temas que había trabajado con Fuensantandreu y con Vicent Caselles era un tema que podía entender todo el mundo porque tiene una historia detrás. Entonces dedicaré una mitad de tiempo a hablar de historia y al final hablaré de nuestros resultados sin entrar en tecnicismo. Yo creo que todo el mundo, cualquier matemático, lo va a poder entender. Yo no he tenido la suerte, como el profesor Mingione, de conocer a Olga Ladyzhenskaya. No tuve la suerte de conocerla, pero tuve la suerte de que escribiera grandes monografías, sobre todo esta de aquí. Esta de aquí la he usado fuertemente, como todo el mundo que... Creo que todo el mundo que ha estudiado ecuaciones parabólicas no lineales ha tenido que usar en algún momento la Ladyzhenskaya. Y si alguno no lo ha usado, es posible que haya publicado un trabajo que está en uno de los teoremas que hay. El problema de ese libro es encontrar... Está escrito de forma que para encontrar el teorema que tienes que aplicar es realmente difícil. Pero bueno, después de poner muchos papelitos y tal, al final lo encuentras. Entonces, como os he dicho, lo que voy a hablar es del problema de la velocidad de propagación. ¿Qué?
¿Cuántas páginas tiene?
Más de 500 y pico, es un tocho.
Es que no lo parece en la foto.
Sí, más de 600. Bien, entonces, es decir, las ecuaciones de difusión aparecen en la modelización de fenómenos físicos, químicos, biológicos, pero no solamente en este tipo de fenómenos. Por ejemplo, la famosa ecuación que tanta fama tuvo hace unos años de Blaise-Scholl, en realidad es una ecuación de difusión. Lo que pasa es que lo que se difunde son precios, pero son ecuaciones de difusión. Y las ecuaciones de difusión lineales, tienen el problema de que, como veremos dentro de poco, que implican velocidad de propagación infinita, lo cual físicamente pues, no tiene ningún sentido. De todas formas, aunque implican esta anomalía física, se usan y se siguen usando en modelos de difusión porque son una buena aproximación a la realidad. La justificación cuantitativa es que las soluciones, aunque empezando con una distribución con soporte compacto, instantáneamente son positivas en todo tiempo, las colas pueden ser muy pequeñas. Pero esto pues tiene sus problemas. Por ejemplo, desde un punto de vista cualitativo, la concentración se va recibiendo, se va acumulando y puede ser significativa. Pero ese no es el problema más grande de la difusión, la ecuación de difusión lineal. El problema más grande está en problemas biológicos, porque hay fenómenos biológicos, como veremos, como el transporte de morfógenos, donde aunque la concentración sea muy pequeña, invalida biológicamente el modelo. Eso lo veremos al final de la charla. Okay. Bien, ¿cuándo empiezan las ecuaciones de difusión? Empiezan con este señor, Joseph Fourier, que he visto que también dedicaste un año, por supuesto, a Fourier. Fourier presentó en la Academia de Ciencias de París en 1804 un trabajo sobre la propagación del calor en los cuerpos sólidos. Y este trabajo, la gran Legendre y no me acuerdo el otro, se opusieron, decían que el trabajo no tenía rigor. Entonces propusieron el premio que la Academia de Ciencias daba cada 4 años, propusieron que para el siguiente premio sería justamente el problema de difusión del calor. Y de nuevo, en el 1807 presentó otro trabajo, no este trabajo, sino modificado, y de nuevo le dieron el premio, pero Laplace y estos matemáticos decían que no tenía rigor. Pero no es que no tenía rigor, el problema no es que no tenía rigor, el problema es que era un adelantado de su tiempo. Entonces, el problema es que tuvo que desarrollarse prácticamente casi todo el análisis del siglo XIX para poder justificar lo que Fourier no justificaba. El caso más paradigmático es la integral. En los trabajos estos en la época no existía ni la integral de Cauchy ni la de Riemann. Cauchy hizo una primera aproximación. Riemann, mucha gente estudia en primero la integral de Riemann. La integral de Riemann en la tesis es un apéndice pequeñito al final, pero la tesis de Riemann es sobre la serie de Fourier, pero había que definir una integral. Y la historia esta, lo he contado algunas veces, me gusta mucho, pero no es el tema. La historia de cómo desde Riemann se llega a Lebesgue, que ya es lo más, y saca la integral de Lebesgue, que gracias a ella vivimos todos. La tesis de Lebesgue de 1905 desarrolla la integral de Lebesgue, porque uno de los problemas que no justificaba Fourier era que tenía una suma infinita, la integral de la suma de las integrales, es decir, que conmutaba el límite con la integración. Entonces, hasta que se llegó al teorema de la convergencia dominada, al teorema de la convergencia monótona, pues hubo pasar mucho tiempo, pero Lebesgue tuvo la idea de conjunto nulo, que es una idea mágica. Pero bueno, voy a dejar esto aquí. Pero el Lebesgue no es que hizo la integral de Lebesgue por hacer la integral de Lebesgue. Al año siguiente publicó un libro sobre la serie de Fourier, donde desarrollaba el análisis de Fourier ya con una estructura rigurosa. Bien, bueno, y después en el año 22 publicó este gran libro Fourier sobre la propagación del calor. ¿Cuál es la idea de Fourier? La idea de Fourier es lo que se llama hoy la ley de Fourier, que dice que el flujo de calor es menos una constante por el gradiente de la temperatura. Entonces, si se considera la ley de conservación derivada en tiempo de la U más la divergencia del flujo igual a 0, pues se llega a la clásica ecuación del calor lineal. ¿Okay? Unos años más tarde, Adolf Fick pues se dio cuenta que esto no solamente era para el calor, sino cualquier proceso de difusión, si poner agua y echar una gota de tinta o ciertos animalitos que se difunden, todos seguían una ley que él llamaba la ley de Fick, que es la de Fourier. Es decir, tengo la conservación de la masa, UT más la divergencia del flujo de las partículas, en este caso UT es la densidad de partículas que se difunden, entonces la ley de Fick, que es la ley de Fourier, la misma ley de Fourier, llega a la ecuación lineal del calor. Evidentemente es la misma ecuación, vale. Pero no solamente, por ejemplo, esto es menos conocido, Louis Bachelier hizo su tesis en 1900 y el director fue Poincaré, el director de la tesis de Bachelier. Y Bachelier, su tesis se llama Teoría de la especulación, buen título. Introduce el concepto de radiación de probabilidad. Si la probabilidad P del precio X al momento T viene dada por esta derivada de aquí, donde esta P tilde es la probabilidad de que el precio exceda a X. Y llega a la ecuación, la misma ecuación de Fourier, ¿de acuerdo? Parece ser que la obra de Bachelier estuvo olvidada muchos años hasta que Samuelson, el famoso premio Nobel de Economía, lo redescubrió y dijo que las ideas de estas ya venían de Poincaré. Bueno, de Bachelier, que era alumno de Poincaré. Muy bien. Entonces, tengo la ecuación lineal esta, de siempre, y como todo el mundo sabe ahora, yo siempre digo, los alumnos lo saben, pero desgraciadamente hay facultad de matemáticas que un alumno puede acabar matemáticas sin ver la ecuación del calor. Yo siempre he dicho que no, pero yo gasto broma a mi alumno y le digo, si el juez Garzón se enterara, más de uno estaría en la cárcel. Bien, pero bueno, os recuerdo esto que habéis visto en la carrera. La solución de la ecuación esta viene dada por la convolución con el núcleo gaussiano. Entonces, la solución tiene esta expresión. Luego, si parto de un dato inicial con soporte compacto, esta integral me dice que para cualquier instante de tiempo la solución es positiva. ¿De acuerdo? Luego tengo velocidad de propagación infinita. Uno de los primeros en criticar la velocidad de propagación infinita fue Albert Einstein en un trabajo acerca del movimiento browniano. Pero, sin embargo, él mismo, como veremos ahora, llegó a tener que usar la ecuación del calor lineal. ¿De acuerdo? El movimiento browniano lo propuso Robert Brown, y es pues el movimiento errático, las partículas de polen suspendidas en el agua, ¿de acuerdo? Y Einstein, en este trabajo de lo que llaman el año maravilloso, 1905, el movimiento browniano se origina por el continuo bombardeo de los granos de polen por las moléculas del agua que lo rodean. Y esto en su época fue muy importante. Vamos a ver cómo llega él a la ecuación, llega de nuevo a la ecuación del calor, para explicar el movimiento browniano. Supongamos que f de tx es la densidad de partículas brownianas que se encuentran en x en el tiempo t. Entonces, bajo ciertas suposiciones físicas, ahora veremos cómo, Einstein llegó a que esta función de densidad verifica de nuevo esta ecuación unidimensional del calor. Lo que fue importante es que obtuvo que el coeficiente de difusión D viene dado por esta expresión, que es la temperatura absoluta, la K es la constante de Boltzmann, M es la masa de la partícula y beta un coeficiente de fricción. Y esto fue importante porque esta fórmula fue la que usó Perrin en 1908 para determinar el número de Avogadro, que dio lugar a que la teoría atómica se estableciera. ¿De acuerdo? ¿Cómo llega Einstein a esa ecuación? Supongamos que tengo que P es X la densidad de probabilidad de que una partícula browniana se mueva de X a X más Y en el tiempo S. Entonces, pues F en T más S viene dada por la integral, esta de aquí, integral respecto de esa probabilidad. Bien, si hago aquí Taylor, me queda esta fórmula. Y ahora, lo que hace Einstein, bueno, me queda esa fórmula, pero como es una probabilidad, la integral vale 1 y es simétrica, luego el primer momento es 0. Luego, en el fondo, el primer momento lo puedo quitar, en la primera derivada la puedo quitar y me queda esta expresión. Y aquí hace Einstein la siguiente suposición. Einstein hace la suposición de que la varianza de la probabilidad sea lineal en S, en el tiempo. Es decir, que esta integral de I cuadrado sea igual a una constante por S. Y aquí, como veremos después, está imponiendo que la velocidad de propagación sea infinita. Como después lo veremos con paseo aleatorio, se ve mucho mejor. Entonces, si bajo esta suposición tiro el tiempo S a 0, pues se llega a la ecuación del calor. Pero, como veremos, ahí está implícitamente está suponiendo que la velocidad sea infinita. Esto se ve más claro con la forma de deducir la ecuación del calor por paseos aleatorios. Supongamos que tengo un pequeño paso de tiempo y de espacio, y que tengo una partícula que en tiempo cero está en S sub 0 y se mueve con probabilidad 1 medio a derecha e izquierda. ¿De acuerdo? Entonces, si denoto por Pmn la probabilidad de que la partícula esté en la posición m incremento de x en el tiempo n incremento de t, pues tengo que esta función, esta probabilidad cumple que esto es igual a 0 o a 1, y que P en n más 1, Pm en n más 1 es 1 medio del anterior más 1 medio de este. Luego hago cuentas y llego a esta expresión de aquí. Y aquí se asume de nuevo, aquí se asume de nuevo que el incremento de tiempo al cuadrado es lineal, pero el incremento de espacio es lineal con respecto al incremento de tiempo, que es la misma hipótesis que en el caso continuo hizo Einstein. ¿Qué es lo que ocurre? Pues que entonces puedo llegar aquí a esta expresión, tirar límite y llego a que la densidad pues me cumple de nuevo la ecuación del calor. Pero claro, al admitir esto, ¿qué es lo que tengo? Pues que el incremento de espacio partido por el incremento de tiempo es igual a d partido por el incremento de espacio. Luego esta es la misma hipótesis que la hipótesis que admitía Einstein. Luego esto me está diciendo que tiene velocidad de propagación infinita. ¿De acuerdo? Muy bien. Entonces voy a ver ahora algunos intentos de quitar esta anomalía de que la velocidad de propagación en la ecuación de difusión fuera infinita. Uno de los primeros es Cataneo. Cataneo en este trabajo lo que hace es cambiar la ley de Fourier, considera un tiempo de relajación tau, y propone, en lugar de la ley de Fourier, propone esta ley. donde aquí Q de nuevo es el flujo. Y aplicando la ley de conservación, al final, pues llega a esta ecuación que es hiperbólica. Y propone eso como ecuación de difusión. Al ser hiperbólica, se puede probar que esta sí que tiene la velocidad de esta ecuación, viene dada por la raíz cuadrada del k cuadrado, los coeficientes que aparecen en la ecuación. ¿De acuerdo? Luego tiene velocidad de propagación finita, ¿vale? Pero, bueno, en realidad, Cataneo no debía conocerlo, pero esta misma ecuación estaba propuesta por Maxwell bastante antes. En el año 1867 ya la propone como ecuación de difusión Maxwell. Bien, pero en el año 92 Rubin demostró que la ecuación de Cataneo viola el segundo principio de la termodinámica. Con lo cual, pues, se sigue usando. Yo sigo viendo trabajos de físicos que siguen usando lo de Cataneo, pero si viola el segundo principio de la termodinámica, pues no vamos bien. Bien, voy a ver otro intento de solucionar el problema de la propagación infinita. Este se debe a Philippe Rosenau. Philippe Rosenau hace lo introduce de una forma súper sencilla, que lo entiende cualquier persona. Tengo la ecuación del calor y la reescribo como una ecuación de transporte. Luego la velocidad, V de U, viene dada por menos la constante gradiente partido por U. Con lo cual, ahí tengo la velocidad de propagación infinita, me viene de que cuando esto va a infinito, la velocidad va a infinita. Entonces, lo que hace Rosenau es decir, bien, pues voy a cambiar la ley que me da la velocidad. Y la cambia. Lo interesante de aquí es que coge en la ecuación va a aparecer una constante que puede ser la velocidad de la luz, la del sonido, o si estoy estudiando un problema biológico, pues la velocidad máxima a la que se difunde el quimiotractante o lo que sea, ¿vale? Entonces, lo que hace es proponer cambiar esto de aquí por esta relación. Esta relación que tiene un cierto sabor relativista, ¿de acuerdo? Y al cambiar esto, lo meto junto a la ecuación de transporte y llego a esta ecuación. Esta ecuación, que la quiero muchísimo, he trabajado mucho con ella, llega a esta ecuación. Ok, y esta ecuación, en principio, pues, se ve que tiene velocidad, en la constante C me limita la velocidad de propagación, ¿de acuerdo? Es importante porque ecuaciones no lineales que tengan velocidad de propagación finita, hay por ejemplo medios porosos, laplacianos, pero por ejemplo en medios porosos la velocidad de propagación depende del gradiente de la concentración. Lo bueno que tiene esta ecuación es que, como después veremos, es que la velocidad máxima me la da la constante que yo pongo. Entonces, si estoy estudiando un problema biológico, eso digo, pues esto no va a mayor velocidad que tal. Lo pongo en la ecuación, fijo cuál es su velocidad máxima de propagación. En medios porosos tú no puedes controlar porque depende del gradiente de la concentración. ¿De acuerdo? Bien. Brenier no conocía, supongo, el trabajo de Rosenau. Supongo que no lo conocía porque, bueno, en un congreso hubo una disputa increíble porque estaba Rosenau y una alumna de Brenier, Marjolaine Poel, habló de la ecuación esta y dijo, Brenier propuso la ecuación y Rosenau, no sé si lo conocéis, levantó la mano. Esa ecuación es mía, esa la descubrí yo en el año no sé cuánto. Además me acuerdo que dijo, a Brenier, ¿quién se la ha dicho? ¿El Espíritu Santo? Esa es mi ecuación. Montó un follón, no sé si conocéis a Rosenau, pero es todo un personaje. Y Brenier la redescubrió, pero con un método totalmente distinto, por medio del transporte de masas de Mons-Cantorowicz. Y Brenier fue el que la denominó ecuación relativista del calor, aunque no es relativista porque no es invariante de Lorentz. Pero él eso tiene un sabor, ¿no? Sabor relativista. Bien. ¿Cómo la sacó Brenier? En el año 98, Félix Soto se dio cuenta que muchas ecuaciones de difusión se podían reescribir como gradiente de la entropía respecto a un transporte. ¿De acuerdo? Por ejemplo, la ecuación de un trabajo con Kinderlege, Jordan y Otto, donde es decir, todo el mundo sabe que la ecuación del calor es el flujo gradiente de la energía de Dirichlet respecto de la norma L2. Pero ellos lo que vieron, interpretaron de forma distinta, usando como distancia la distancia de Weierstrass 2 y como energía la entropía de Boltzmann. Ahora explicaré esto con más detalle. Y este fue el camino que siguió Brenier. Bueno, las ideas de Félix Otto en este trabajo de Martial Aguet se estudian en un contexto mucho más general. Martial Aguet lo que estudia es ecuaciones de esta forma de transporte, donde la velocidad, si tengo la ecuación de transporte, V es la densidad, V es la velocidad. La velocidad viene dada como menos gradiente de K estrella gradiente, la explicaré qué es cada cosa de esta de aquí. ¿De acuerdo? La K estrella es la transformada de Lejeune-Frenchel de la función K, que viene definida de esta forma. Y la función K es la que está asociada al coste del proceso de transporte. Y la F que aparece aquí, F', la integral me da la energía. Entonces, vamos a ver que muchas ecuaciones clásicas se pueden escribir de esta forma, con este formalismo. Por ejemplo, la ecuación del calor. Si considero como K, como el coste, módulo de z al cuadrado partido por 2, y como energía la entropía de Boltzmann, entonces lo meto en la ecuación general y me da la ecuación lineal de difusión. Medios porosos también se puede hacer. La función coste es la misma. Esta función coste da lugar a la distancia en las probabilidades a la distancia de Weierstrass 2. Lo que pasa que aquí la entropía cambia, no es la entropía de Boltzmann, sino esta entropía que no me acuerdo del nombre del señor, pero tiene un nombre. Pero pelaplaciano también se puede escribir tomando, ahora aquí cambia hay que usar la Weierstrass P', si la P de la ecuación pelaplaciana es P. Y cambia también la entropía. ¿Okay? Entonces lo que hace Brenier es decir, bueno, dice, voy a considerar como K, que es la que me da el coste, voy a considerar esta función. Y esta función me está diciendo que si voy a velocidad mayor que la C que he fijado, si va a velocidad mayor, pago infinito. Me tiene que dar una ecuación de difusión que no pueda pasar la velocidad de la C que pongo aquí. ¿De acuerdo? Usa la entropía de Boltzmann. Entonces, si esta es la K, calculo la transformada de Frenkel, me queda esto, la V me da esto, y de nuevo, mágicamente, aparece la misma ecuación que había sacado por unos métodos distintos Rosenau, Philippe Rosenau. ¿De acuerdo? Bien. El propio Brenier lo que hizo fue proponerla. Es decir, bueno, si yo pago infinito, la ecuación de difusión que me va a salir es esta, pero no la estudió. Bien. Pero él mismo dice que estas ecuaciones, había muchas ecuaciones parecidas de estas, sobre todo en teoría de la radiación hidrodinámica. Dice que es una de las muchas que ya los físicos usaban como limitador de flujo. El limitador de flujo lo que dice es que la densidad de energía por la velocidad de la luz no puede exceder la velocidad de propagación. Es decir, no se puede violar la causalidad. Una de las... En radiación hidrodinámica hay varias, pero este limitador de flujo lo propuso un tal Wilson, y se ve que en este caso C es la velocidad de la luz, y da lugar a una ecuación que es muy parecida. Matemáticamente esto y esto para nosotros es lo matéis. No hay un problema. Pero hay más ecuaciones. Bueno, entonces, hace unos años nos propusimos, Fuensanta Andreu y Vicent Caselles y yo, estudiar un tipo general de ecuaciones que tuviera como caso particular la relativista del calor, la ecuación de Wilson y más ecuaciones que tienen limitador de flujo. Y en estos dos trabajos, los primeros que hicimos, estudiamos el problema de Cauchy. En general, lo que estudiamos es un problema de este tipo. la parcial de u con respecto al tiempo, divergencia de un A de x de du, y este A es el gradiente de un cierto lagrangiano f. Y el lagrangiano f tiene crecimiento lineal en infinito. Y una serie de hipótesis, que no he dicho que no quiero entrar en tecnicismos, una serie de hipótesis que voy a llamar H, ¿vale? Pero si yo tomo como lagrangiano este de aquí, hago las cuentas y el A me queda justamente el de la revista del calor. Y este cumple la hipótesis que nosotros imponemos para tener existencia y necesidad de solución. Si tomo este, me sale la ecuación de Wilson. Pero hay otras ecuaciones, por ejemplo, esta ecuación del plasma, que también es distinta, pero tiene un cierto parecido, también cae dentro de la teoría general que nosotros desarrollamos. ¿De acuerdo? Bien. No voy a hablar de la prueba ni nada, voy a decir solamente cuáles son las dificultades que tiene. Esta ecuación estuvimos peleando con ella muchísimos años. Las dificultades matemáticas que tiene. Una primera dificultad es que como el lagrangiano tiene crecimiento lineal, no se puede trabajar en el espacio de Sobolev. En el espacio de Sobolev tengo acotación en W11, pero cuando aplico compacidad me voy a BV. Luego voy a trabajar en BV. Y BV son funciones de L1 que cuando calculo la derivada distribucional me da una medida de radón con variación total acotada. Pero entonces, en el gradiente distribucional tengo que considerar tres partes. La parte absolutamente continua con respecto a la medida de Lebesgue, que lo denotaré por nabla de U, la parte de salto de la función y la parte cantoriana. Y eso hace que técnicamente es bastante engorroso trabajar con ello. Pero esta ecuación tenía otro problema, porque con este tipo de funcionales lineales nosotros ya hemos trabajado, por ejemplo, en los trabajos que dimos sobre el uno laplaciano, que antes Albert ha comentado que nos dieron el Ferran, Sunyer y Balaguer, en el que estábamos. Se dice molt pagat. Bé. Pero aquí uno de los problemas matemáticos que tiene es que se pierde la coercividad. Al perder la coercividad tenemos que truncar por arriba y por abajo las funciones y usar truncaturas de este tipo. Luego el espacio de energía que hay que usar es exactamente este de aquí. Bueno, trabajamos con son densidades, funciones positivas de L1 que al truncarla a nivel AB son BV. Con lo cual tuvimos que dar un sentido a la derivada de radón-Nicodim para funciones de aquí, porque para funciones de BV lo tenía, pero no en general aquí. Variación acotada. Bien, pues ahora el problema, si recordáis por ejemplo la ecuación relativista, raíz cuadrada de U, gradiente de U partido, divergencia de U, gradiente de U partido raíz cuadrada U cuadrado, es decir, ¿cómo interpretar ese operador cuando la du, supongamos que la U fuera variación acotada? La du es una medida y ahí arriba tengo divergencia de U frente a du. La U no es continua. Divido por la raíz cuadrada de U cuadrado más. Es decir, lo complicado fue interpretar dar un sentido a este operador. ¿De acuerdo? Para dar un sentido a este operador usamos como herramientas fundamentales una fórmula de Green debido a Ancelotti y desarrollamos un cálculo funcional que está inspirado en unos trabajos de Dalmaso y Dalmaso y antes hemos estado hablando de Pisa, se me olvidó el nombre. Dalmaso y lo que hacen es dar una representación de la energía asociada a los funcionales lineal con crecimiento lineal. Dalmaso y no me acuerdo ahora. Ambrosio me entiende. No, y el otro es que ya me han jubilado y la memoria me está fallando bastante. Butasso, exactamente. Butasso y Dalmaso tienen un trabajo. El primero es de Dalmaso. El primero es de Dalmaso, ¿de acuerdo? Entonces, usando esto, conseguimos dar un sentido a esto. Bien. ¿Cómo probamos nosotros que el problema de Cauchy tiene solución? Usamos la teoría de semigrupos no lineales, es decir, el teorema de Grandal-Liguet. El teorema de Grandal-Liguet, al cual adoro porque lo he usado infinidad de veces para probar existencia de unicidad, viene a decir lo siguiente: yo tengo un problema UT igual a un operador A de U y quiero resolver el problema este. Entonces, no lineal. Considero el problema elíptico asociado. Si el problema elíptico asociado en este caso sería un problema de este tipo: U más el operador multiplicado por un lambda igual a F. Si yo defino un concepto de solución aquí, de forma que esto tiene una única solución, entonces cuando yo discojo el problema parabólico, discretizo en tiempo la derivada y tomo límite cuando el incremento de tiempo se va a cero, eso tiene una solución. Una solución mild solution, muy fea, pero sabes que es una función continua de 0t con valor en el espacio de Banach que estés trabajando, y que proviene de resolver los esquemas. Bien, pues aplicamos Grandal-Liguet y obtenemos solución abstracta, o la gente llama mild solution o solución semigrupo del problema. Y ahora, el teorema de Grandal-Liguet ha tenido mala fama porque hubo una época en que la gente llegaba aquí y decía: solucioné el problema. La solución del problema es la mild solution que he encontrado. Pero la mild solution no es operativa. La mild solution puede ser a lo mejor operativa numéricamente, pero no es operativa para hacer cálculos, ¿de acuerdo?
¿Da existencia y unicidad?
Da existencia y unicidad de mild solution. Pero la mild solution, pues sí, es el límite de la solución de esos esquemas. Entonces, lo más complicado pues que cuando llega tú tienes el problema real, por ejemplo, la ecuación relativista del calor, y quieres dar un concepto de solución y tener existencia y unicidad. Si tú aplicas el mecanismo este y ahora llega aquí y dices: tengo mild solution, y dices: señores, me voy, después no puede operar. ¿Qué es lo que hay que hacer? Pues hay que hacer la parte más complicada. La parte más complicada es: ahora cojo el problema real que tengo, la EDP real, y debido a las ideas que me ha dado cómo defino el operador, doy un concepto de solución de la ecuación esta, un concepto de solución, entrópica, lo que sea, ¿vale? Probamos que ese concepto de solución, esta ecuación tiene una única solución. Y esta es la parte más complicada porque hay que usar desdoblamiento de variables de Kruskov, pero aquí, como he comentado antes, la derivada tiene 3 partes y es bastante delicado. Pero finalmente probamos existencia de solución. Y después probamos que las soluciones de entropía que hemos definido del problema real coinciden con las semigrupos. Por unicidad de las dos, acabé. Pero entonces ya el teorema de Grandal-Liguet, después de hacer esto, ya te dice que ese problema real tiene una única solución de entropía. ¿De acuerdo? Eso es lo mismo que si, por ejemplo, está con Hamilton-Jacobi. Lo estudias bajo el punto de vista de semigrupos. Y después hay que ver que la solución que te da es la solución de viscosidad. ¿De acuerdo? Bien. Bien, no sé cómo voy de tiempo. Me queda un cuarto de hora. A ver si me da tiempo a hablar de todo. Bien, siguiente paso que hicimos. Bueno, técnicamente es complicado porque la derivada temporal, en principio, no es una función integrable. La derivada temporal, por si hay alguien por si hay alguien en la audiencia de funcional, la derivada temporal, en principio, aquí se puede escribir, UT pertenece a L1 0T dual. Es una porquería. Es una porquería porque además esto no es L infinito 0T dual, son mentiras. Pero hay unos trabajos viejos de los Gannes-Bar que estudian en general duales de este tipo. Bien. El siguiente paso que hicimos fue, pues bien, ya tenemos el problema está bien puesto, vamos a probar que efectivamente esa ecuación tiene velocidad de propagación finita, dominada por la constante c. Esto fue lo más complicado, este trabajo de Archaeological Mechanics, porque finalmente lo probamos, pero la prueba es muy delicada porque el concepto de solución es jodido y lo hicimos. Buscar una super solución no es difícil, pero buscar una solución que te ajuste, que no pasa de la velocidad c, es bastante fino. Pero efectivamente probamos que yo empiezo, es decir, bueno, después hay dibujitos, creo que tengo dibujitos. Empiezo con una función de soporte compacto y eso va a velocidad, se expande a velocidad c. Vale. Luego, evidentemente, aquí tengo los dibujitos numéricos. Esto es el dato inicial y esto empieza a formar aquí una pared vertical, va a velocidad la que le he puesto, en este caso 1, y va formando va desarrollándose de esta forma. ¿De acuerdo? Si parto de un dato inicial que sea de esta forma, pues numéricamente se ve que se va formando esto de aquí hasta que se une y ya cuando tiene esta forma sigue. Pero es importante que tiene un frente de propagación vertical. ¿De acuerdo? Bien. En este trabajo lo que hicimos fue estudiar una especie de medios porosos, añadirle aquí U a la M. Añadirle U a la M, como esto cae dentro de la teoría general nuestra, es de la forma un A de X de U. Pero aquí lo que estudiamos fue ver cómo era la evolución. Y aquí, cambiando el M con M mayor que 1, la evolución es bastante distinta. Aquí está la explicación, pero voy a poner el dibujito y se verá mejor. Lo que ocurre aquí es que parto de este dato, en principio no se mueve, hay un waiting time, porque ocurre típico en las ecuaciones de medios porosos, se va deformando aquí y me crea una discontinuidad. Y una vez que ha creado la discontinuidad, entonces ya vuelve a expandirse a velocidad controlada por c. ¿Cuál fue el siguiente que hicimos? Estudiar la regularidad. Y aquí usamos el libro de Ladyzhenskaya para tener regularidad. Porque la ecuación está, como habéis visto en los ejemplos, es decir, fuera del soporte vale 0 y hay una discontinuidad. Pero la ecuación esta, que en realidad es hiperbólica parabólica, vemos que dentro es parabólica. No es fácil, pero usando resultados de Ladyzhenskaya conseguimos probar el siguiente resultado, admitiendo, por supuesto, que el dato inicial tenga buenas propiedades. Entonces, hicimos un cambio de variable, aparece una ecuación a la que le pudimos aplicar resultados de Ladyzhenskaya y probamos que tiene bastantes propiedades buenas. Por ejemplo, ya en tiempo ya no es esta porquería, ya es BV en tiempo, es decir, la derivada en tiempo es una medida. Y dentro del soporte es incluso C infinito. ¿De acuerdo? Y el ángulo de contacto es vertical, como se ve, esto lo probamos bien.
¿Cuál es el cambio?
Es con una exponencial, pero ahora no me acuerdo.
Ah, pero es local.
Sí, es un cambio, entonces aparece una. No me acuerdo del cambio ahora, no me acuerdo del cambio.
Pero es uno lineal.
Perdonadme, es que ya he cumplido 70 y la memoria me falla bastante. Me ha fallado toda la vida, pues ahora más. Bien. Voy a hablar ahora de ecuaciones de reacción-difusión. La ecuación de reacción-difusión, la primera, la más famosa, es la denominada de Fischer-Kolmogorov, que esta ecuación es muy sencilla, que tengo una difusión lineal y aquí tengo este tipo de reacción. ¿De acuerdo? ¿Cómo?
Y también fueron matemáticos de la FME.
Exactamente. Esto Fischer lo propuso en el año 37 para considerar como modelo para la dispersión de un gen favorable. Pero sobre los mismos años, Kolmogorov, no solo Kolmogorov, es un trabajo de Kolmogorov, Piskunov y Petrovsky, exactamente, tiene más memoria que yo, y Petrovsky. Estudiaron una ecuación parecida donde aquí era una f de u, que prácticamente, este es un ejemplo de los más importantes. Entonces, en la literatura, no sé por qué, a Petrovsky a nosotros lo han quitado y todo el mundo le llama Fischer-Kolmogorov. Yo en la literatura.
Bueno, cuando dicen que esa es la ecuación de KPP,
Sí.
todo el mundo le dice KPP. Bueno, gente le llama
KPP, vale.
Los franceses le llaman KPP.
Sí, no, sí he visto, sí, le llaman
Ya
KPP.
no dicen.
Ok. Fischer-Komolov, esta ecuación. Esta ecuación tiene una particularidad importante, que es que tiene ondas viajeras. ¿Qué es una onda viajera? Una onda viajera es, considero una solución particular que sea un perfil y pongo aquí v, función de x, menos sigma t. Pero es conocido que la tasa de... Esto me da la onda, como se va propagando, tiene que ser mayor o igual que esta cantidad de aquí. Pero ese no es el mayor problema, porque estas ondas viajeras, la gente dice, bueno, es una onda que se mueve a velocidad sigma. Pero como tengo la difusión lineal, en el fondo, esto será algo así, esto irá a la velocidad esa, pero esto no es cero. Eso no es cero porque tengo difusión lineal, ¿de acuerdo? Entonces lo que hicimos fue intentar estudiar en este trabajo, en colaboración como siempre con Fuensanta y Guillén, estudiar la misma ecuación pero cambiando la difusión lineal por la relativista del calor. Y para esta ecuación probamos que efectivamente va a velocidad c, es una fuente, pero es cero a partir de un tiempo. Y un poco tiempo después, en este trabajo de Campo, Guerrero, Sánchez y Soler del grupo de Granada, estudiaron las ondas viajeras de esa ecuación. Y la onda viajera aparece en casos muy sintomáticos. Hay un parámetro, sigma estrella, de tal forma que cuando la velocidad de la onda, no la velocidad de propagación, sino la velocidad sigma, la velocidad de la onda, es mayor o es igual y es menor que la velocidad de propagación, pues tengo soluciones de este tipo. Pero cuando la velocidad de la onda es la misma que la velocidad de propagación, aparecen soluciones de entropía, aparecen soluciones que en realidad aquí una onda que se va moviendo, pero aquí hay cero, que es lo más realista que sea positivo. Bien, el señor Turing es súper conocido por todo el público, yo creo que, bueno, ya no por la película, pero todo el mundo, cualquier persona más o menos culta con Turing, la máquina de Turing, el que descifró la máquina de los nazis, pero hizo cosas también muy importantes que son menos conocidas en biomatemática. Fue uno de los pioneros en biomatemática, en este trabajo sobre la química de la morfogénesis. En este trabajo lo que propone son ecuaciones de reacción-difusión para explicar la formación de patrones, ¿de acuerdo? Entonces, ¿qué son los morfógenos? Los morfógenos son unas sustancias, proteínas, que gobiernan el patrón de desarrollo tisular. Es decir, por ejemplo, cómo se forman los dedos, o cómo, es decir, eso viene dado por la información genética que llevan los morfógenos cuando tocan las células, ¿de acuerdo? Sí, el color de las cebras. Bien, entonces el morfógeno está en la célula. Hay una fuente donde el morfógeno toca la célula, hay una reacción dentro de la célula, sigue el morfógeno, ¿de acuerdo? Y la velocidad de propagación, es decir, hay un montón de modelos donde para la difusión del morfógeno usan la difusión lineal, pero los biólogos se dieron cuenta de que en este caso es que invalida totalmente el modelo, porque se dieron cuenta que la concentración recibida por la célula y el tiempo de exposición son igual de relevantes. Entonces, si yo sufro el morfógeno y aunque sea poco morfógeno me llega a toda la cantidad de células, le está dando una información que en realidad no es la real. La real es que va a una cierta velocidad súper finita, ¿de acuerdo? Bien, en este trabajo del grupo de Granada, y algunos que son de Madrid, me parece, y hay otro señor que tampoco es de Granada, tampoco es de Granada, lo que hicieron fue estudiar numéricamente, propusieron un modelo que era los modelos que habían sobre morfógenos, pero cambiando la difusión lineal por la relativista, colocando la constante C, una constante que ellos más o menos sabían que era la adecuada. Y los resultados que obtuvieron fueron bastante... Este es el modelo. Lo hacen sobre la formación de... Yo le pregunté... es la formación de la columna vertebral de un pollo. Porque el Sonid GG Hop, es un morfógeno que es el que hace cómo se va formando la columna vertebral de un pollo. Entonces ellos suponen matemáticamente que la columna vertebral es un 0L, suponen que la columna unidimensional, tengo 0 hasta L, y aquí yo le estoy metiendo el morfógeno, toca la célula, hay reacciones y va avanzando, ¿de acuerdo? La formación de la columna vertebral. Bien, entonces esta es la ecuación. Esto es la relativista del calor y hay unos términos de la reacción de cuando el morfógeno entra en la célula, hay una reacción, ¿de acuerdo? ¿Cómo?
¿Hay un delay?
Sí, hay un delay. Bien, entonces nos propusimos estudiar este modelo matemáticamente sin la reacción, porque nosotros habíamos estudiado, bueno, hemos estudiado el problema de Cauchy, también estudiamos el problema de Neumann y estudiamos el problema de Dirichlet. El problema de Dirichlet, ahora lo veréis posiblemente aquí al final, el problema de Dirichlet tiene la particularidad de que el dato Dirichlet no se toma casi por todas partes en el borde. El dato Dirichlet se toma de una forma débil. Bueno, ahora lo veréis. Entonces, nos propusimos en este trabajo estudiar este problema. Tengo una condición Neumann igual a beta, es decir, en el 0 le estoy metiendo el morfógeno y se desarrolla. Entonces probamos pues que hay una única solución de entropía del problema este de aquí y le pongo un Neumann igual a beta en el 0 y un Dirichlet igual a 0 en el borde, en la otra parte. Y en este trabajo vimos que efectivamente va a velocidad c. ¿De acuerdo? Lo hacemos también igual que antes por comparación con sub y supersoluciones. Esto es numéricamente, una de los tres autores hizo el numérico, esto es lo que da, pero donde se ve claramente la importancia es aquí. Aquí estoy comparando, tengo 0, estoy metiendo el morfógeno por aquí y en rojo tengo la solución que da usando la relativista del calor y en verde la ecuación lineal. Si veis, con la ecuación lineal instantáneamente el morfógeno ha llegado a todas las células. Eso es lo que los biólogos decían que no tiene ningún sentido. Sin embargo, aquí veis cómo va y cuando llega ahí no toma el 0, sino que toma el 0 de una forma débil que nosotros definimos que una cierta traza cumple una condición de Neumann. ¿Ok? Bien, pues ya con esto casi acabo. Sí. También estudiamos el problema estacionario y vimos que la solución del problema converge al problema estacionario en la norma L1 y esta es la única solución de entropía del problema estacionario. Y me parece que con esto, sí, ya solamente daros las gracias por la atención.
Muchas gracias. No sé si alguien tiene alguna pregunta o alguna contribución que hacer. Sí, Joan.
Mazón, muchas gracias. Ha sido un panorama muy amplio, muy interesante. Muchas gracias por la explicación. Yo quisiera hacerte una pregunta, que es la siguiente, un poco filosófica. Se me ha suscitado cuando has hablado de vuestros trabajos con la ecuación relativista del calor y con la generalización de la ecuación relativista del calor. Porque has dicho, bueno, el primer problema aquí es interpretar qué quiere decir solución. Esto es lo que, tal como lo has dicho. Porque claro, una función de variación acotada, que allá se le hace la divergencia, se la multiplica por no sé qué, muchas cosas hay, ¿no? Bueno, yo creo que yo opino, y seguro que tú también, pero quiero saber tu opinión, yo creo que esta es una característica de las ecuaciones en derivadas parciales del siglo XX, en la cual la Ladyzhenskaya también tuvo importante contribución, especialmente las ecuaciones de Navier-Stokes, que es interpretar las soluciones en un sentido laxo, que permiten el análisis funcional y permiten muchas cosas. Pero lo que pasa es que tú y todos todavía seguimos escribiendo las ecuaciones como si fuera aquí derivo respecto al tiempo y aquí derivo respecto a X. No nos deshacemos de esto, aunque la solución débil, la solución distribucional, la solución de entropía, la solución aquella otra, la de viscosidad, claro, pues son, yo qué sé, cosas raras, cosas raras.
Pero son únicas, luego son las reales.
Bueno, esto quería saber, ¿qué es lo que piensas tú de esto?
Sí, cuando he hablado sobre esto a la tribu, los que son de la misma gente de la misma tribu, a veces he cometido el error porque aunque sea de la tribu ya tiene muchas subtribus. Entonces hay uno que puede que sepa de parabólicas pero no sepa de hiperbólicas. Entonces es decir, que ya somos dentro de la tribu, hay bastantes subtribus. En las primeras charlas cometí el error de intentar dar la definición de solución. Pero el problema es que para dar la definición de solución gastaba media hora, porque tenía que dar una cantidad de definiciones de qué es lo que entendía por esto, qué es lo que entendía por otro. Al final la gente ya no sabía de dónde estaba, porque el concepto de solución realmente es complicado. Lo que pasa es que después como hemos visto, en el fondo se reduce todo a que dentro del soporte es una ecuación parabólica perfecta y vale cero, tiene un frente perpendicular que se va moviendo a velocidad c. Pero claro, el aparataje matemático que hace falta para que eso, porque para obtener unicidad, como he dicho antes, usamos el método de desdoblamiento de variables de Krusskov, que es técnicamente muy complicado, pero es técnicamente complicado si lo haces para ley de conservación. Pero aquí es que en la derivada tengo la parte absolutamente continua respecto al Lebesgue, la de salto y la cantoriana. Y cada una necesita una técnica distinta cuando le aplico el desdoblamiento de variables de Krusskov. Entonces, técnicamente es complicado. Pero tengo existencia de unidad. Yo recuerdo Juan Luis Vázquez, la primera vez que le conté esto en un congreso de Estado, y dice: Mazón, eso es muy difícil, eso es muy complicado. Y dije: Juan Luis, lo siento mucho, pero tengo existencia de unicidad y te pruebo que se mueve a velocidad que me da c. Yo no tengo culpa que las cosas sean. Ese concepto de solución, eso es imposible. Digo, pues lo siento, Juan Luis, pero es lo que hay.
La unicidad solo se puede demostrar con este método.
Con Krusskov.
Que es como el de Ischi de viscosidad.
Sí, bueno, Ischi de viscosidad está basado en la idea en Krusskov. Pero el primero que hizo eso fue Krusskov, que era un genio. Y la usa ya muchísima gente. Uno de los que más ha usado eso de forma interesante es Carrillo, no José Antonio. Carrillo, el hijo de Pepe Carrillo. Pepe Carrillo era después se metió a rector, pero tiene trabajos muy potentes de usar el método Krusskov. Porque Krusskov era muy amigo de Philippe Benirán. Y te conocí en el congreso sobre Krusskov que organizó Philippe en el año, no me acuerdo, hace mucho. Pero no entiendo, es decir, ¿estás en contra de usar las soluciones débiles o no? Ah.
Yo destaco este fenómeno.
Sí.
Del movimiento de líquidos viscosos. Es una cosa muy antigua, Pero empieza cargando, dice, bueno, yo os voy a dar soluciones que veréis lo que son. Las soluciones débiles de la Ladyzhenskaya o de Lerey, que fue quien se las inventó. Esto yo lo dejo para otra gente, ¿no? Pero bueno, yo quería preguntarte no sé, ¿qué opinas de cómo han evolucionado estas cosas?
Es que he estudiado ecuaciones que son muy degeneradas, no sé por qué, pero son muy degeneradas.
¿Alguien tiene alguna pregunta más? ¿Alguna contribución que hacer? No, pues agradecemos a Mazón por su fantástica charla.
Muy bien.
Bon dia a tothom. Tot seguit anirem a procedir al lliurament dels premis del concurs Ladyzhenskaya, perdó, és que costa una mica pronunciar aquest nom. A veure, des del curs 2013-14, ja gairebé l'any que ve farà 10 anys, la biblioteca de la FME organitza conjuntament amb les professores de l'assignatura Història de la Matemàtica un concurs relacionat amb la matemàtic del curs que designa la FME, escull la FME. Per tant, aquest any aquest concurs està dedicat a la Olga Ladyzhenskaya, ara ho he dit bé. El concurs té diversos objectius. Un d'ells és donar a conèixer la vida i l'obra en aquest cas la matemàtica, o sigui la Olga Ladyzhenskaya, entre la comunitat FME, i especialment pels estudiants. I també fomentar la cerca d'informació sobre la matemàtica, d'informació de fonts i recursos que estan disponibles a les biblioteques de la UPC. Per exemple, el portal del matemàtic, que és aquest que teniu ara aquí a la pantalla, i també el catàleg de les biblioteques de la UPC, revistes, bases de dades, tot el que us puguem donar. El concurs es va fer ara el mes d'abril, entre el 13 i el 24, i s'ha gestionat a través d'una xarxa social, especialment, que és Instagram, que és allà on els nostres estudiants estan presents. Ara, d'aquí un temps ja veurem on estaran i, per tant, haurem d'anar evolucionant. S'han fet 4 preguntes a l'Instagram de la biblioteca i les preguntes es van fer relacionades amb les aportacions o algun esdeveniment relacionats amb la Olga Ladyzhenskaya. Per exemple, quina aportació més rellevant va fer la Olga a la mecànica de fluids o, per exemple, quin prestigiós premi va guanyar el 1969. Totes aquestes preguntes i respostes i guanyadors estan aquí a la web de la matemàtica, enllaços d'interès, hi ha una pàgina dedicada al concurs. Aquí trobareu tant totes les bases del concurs com totes les preguntes que s'han fet, les respostes i els guanyadors. El premi que es donarà als que han guanyat cada una de les preguntes és un llibre, és aquest llibre de la Jacqueline Estedal, ara la Mònica, que la Mònica la coneixeu, és la professora, una de les professores de l'assignatura Història de la Matemàtica. Si vols, sí.
Bon dia a tothom. La coordinadora de l'assignatura és la Maria Rosa Massa i avui no podia venir, si no estaríem les dues, bueno, les tres, amb la Gemma, exacte. El llibre en què consisteix el premi és aquesta història de les matemàtiques de Jacqueline Estedal, que és un llibre que ja fa uns quants anys que és el premi del concurs. És un llibre que ja veieu que és molt primet, no és l'habitual en els llibres de història de les matemàtiques. És un llibre que de fet va guanyar el premi de la Societat Matemàtica Britànica, crec que el 2012-2013, i és un llibre que tant a la Maria Rosa com a mi ens agrada molt perquè dona com un enfocament diferent a la història de les matemàtiques, tenint en compte això, que la història de les matemàtiques no és una història lineal, no és de punts aïllats, no és una col·lecció de punts aïllats, i dona molta importància al que seria la circulació del coneixement i tots els agents que estan implicats amb el desenvolupament i la circulació de les idees matemàtiques, tant des del punt de vista per exemple, dels lectors, dels autors de llibres, des del punt de vista de comerciant, per exemple, també des del punt de vista econòmic, o sigui, diferents factors, diferents agents que en un llibre estàndard, podríem dir, de història de les matemàtiques no apareixen, i per això, i perquè ens agrada molt aquesta historiadora de les matemàtiques, que malauradament ens va deixar fa relativament poc, Jacqueline Stedal. Sí, no sé si surt el... Sí. Sí, és una delícia de llibre. Sí. Sí. És que aquest és un dels punts del llibre, que no té un scope, un abast típic, sinó que potser això comença amb... Hi ha un dels capítols que m'agrada, més a història a vegades ho comentem, la circulació, la generació, per exemple, dels numerals a l'Índia, i com finalment es traslladen i a través d'aquí es traslladen i arriben a Occident. I per tant és un abast ben ampli. Per tant no és un període concret, no és d'una matèria en concret, sinó fa com diferents estudis de casos al llarg del temps i al llarg de la geografia i al llarg de la geografia matemàtica també. I per tant és un llibre que tenim a la biblioteca gràcies a la Gemma i que jo us recomano i que és una elecció que vam fer la Maria Rosa i jo fa un temps perquè ens agrada el llibre i perquè ens agrada aquesta historiadora de les matemàtiques. I gràcies, Gemma, per tota la feinada.
Bueno, abans de donar els premis, als guanyadors, vull donar especialment les gràcies a tots els participants. Hi ha 4 guanyadors, però en participants més gent. I en segon lloc també donar les gràcies a les professores Mònica Blanco i Maria Rosa Massa per la seva col·laboració, especialment en el plantejament de les preguntes que les han fet elles. I ara sí, procedim a donar els premis als guanyadors. Algun guanyador em sembla que ja s'ha disculpat que no podia assistir per motius personals, però 3 em sembla que estan aquí a la sala, que ja els veig ara, i els anirem cridant un a un i els hi anirem donant el llibre. El guanyador a la primera pregunta, us poso en pantalla quines eren les preguntes i així també les podeu veure exactament què és el que preguntaven. La primera guanyadora, la primera pregunta és la Clàudia Ramírez, estudiant del grau de matemàtiques. Si vols pujar, Clàudia. El guanyador a la segona pregunta és l'Adrià Ferrer, també estudiant del grau de matemàtiques. Felicitats. La guanyadora a la tercera pregunta és la Joana Pec i malauradament no ha pogut venir i vindrà a recollir el premi a la biblioteca. I el guanyador, la quarta pregunta, és el Jordi Lluc, estudiant també del grau de matemàtiques. Molt bé, moltes felicitats. Bueno, i fins aquí moltes gràcies a tothom i esperem que la participació massiva d'estudiants pel proper concurs, que serà l'any que ve. Molt bé, gràcies.
Bé, crec que podem començar ja amb aquesta segona xerrada en aquesta sessió sobre Olga Ladyzhenskaya. It is my pleasure to introduce Professor Stefania Cherubini. Stefania studied mechanical engineering at the Polytechnical University of Bari, the Polytechnical di Bari, and after she received 2 PhD degrees, one in Italy from the same Polytechnical di Bari, and another one from the École Nationale Supérieure d'Arts et Métiers de Paris, where she has spent several years. From 2012 to 2016, she was maître de conférences at the Laboratoire de Dynamique des Fluids de l'École d'Arts et Métiers de Paris. And from 2016, she is an associate professor in fluid machinery at the Polytechnical University of Bari. Stefania has received several awards related to fluid mechanics. For instance, she was awarded, or she was finalist of an award of the Leonardo da Vinci Award of the ERCOF-TAC. The ERCOF-TAC is the European Research Community on Flow, Turbulence and Combustion. It's an European association which is related to, essentially, to turbulence and combustion, essentially. And she also was awarded the IMETA Junior Prize for Fluid Mechanics. The IMETA is the Associazione Italiana di Meccanica Teorica e Applicata. She has published many papers, about 50 papers, most of them in the main journals in fluid mechanics, which is not easy to do, I can tell you. And these publications cover different topics. One of them, transition to turbulence in shear flow, is the subject of her talk of today. But there are other topics in which she has published. One is in hydrodynamics, and one of the topics can be hydrodynamic stability, thermoacoustic instability, wind turbine flows, for instance, and many other applications of fluid mechanics. The title of the talk of today will be Characterize and Control Turbulence in Shear Flows via Nonlinear Optimization. So it is your time, Stefania, if you can share your talk.
Okay. Oh. Doing the sharing, and I think you must see it. Okay. Can you see the screen?
Yes, we can see the talk.
Okay, perfect. So thank you very much for the invitation, and sorry for not being there in person, but I think you know I had a family grief, but I thought it was important to keep the talk and do it anyway. And I will talk today about my work, the last 10 years of work, more or less. I tried to do that in a divulgative way, so in order to make you understand. I will try to say you something about the characterization and hindering of turbulence in simple flows. And we will do that using, of course, the Navier-Stokes equation and nonlinear optimization. Okay. So first, since we're interested in laminar and turbulent flows, I will say you something about what is a laminar and turbulent flow. So the typical example is that of the smoke of a cigarette. So the initial part of the smoke of a cigarette is a laminar flow, so a flow in which the fluid particles follow parallel layers and they're ordered. They follow an ordered motion. And then you can see here some vortices that appear, and then the flow really becomes turbulent. So we have many little vortices that develops with a a chaotic behavior. So if we measure here the velocity and the pressure, it will follow a chaotic oscillation with a typical spectrum of frequencies. And why it is important whether the flow, a given flow may be laminar or turbulent. So the importance is that the resistance of an object within the flow, immersed within the flow, increase very much when the flow is turbulent. So here you can see a typical example of the flow of a flat plate impinged by a flow, normal flow. So it can be the model of a wing or whatever object immersed in a flow. And in the beginning, you can see that the flow is laminar. It follows parallel layer. It is an ordered motion without vortices. And the drag, so the resistance of the flow to the flat plate is low. And then when there is this transition to the turbulent regime, we see the resistance that increases suddenly, and then it remains high when the flow is turbulent. So if we want to keep the resistance to the fluid low, so in order to save energy, for instance, if I want to simply move a fluid within a pipe, within a channel, if the flow stays laminar, I will use less pressure and so less energy to move the fluid. So we are interested in keeping the resistance low, and so trying to know at least when this flow can stay laminar in order to reduce this resistance. And so the first one that asks himself when the flow becomes turbulent, it has been an experimentalist, Osborne Reynolds, in hundreds of years ago. And so he made some experiments on the flow in a pipe, so in a circular section pipe. He simply puts a dye, an ink dye, within the flow, and in the beginning he keeps the velocity very low, and you see that the dye goes straight here in, of course, parallel layer, so the flow was laminar. And then when he increases the velocity of the flow, you see that the flow started to create some vortices, but still wasn't really turbulent. And then increasing the velocity to higher values, he observed a turbulent flow. And so he did that for several pipes of several diameters, etc. And he saw that the transition depends on this non-dimensional number, which is called the Reynolds number after his name. That depends on the velocity, on the length scale, so in this case, the diameter of the pipe, the density, and the viscosity of the flow itself. And so if the Reynolds number is low, the flow stays laminar. If it increases, it experiences transition. And when the Reynolds number is high, we have a turbulent flow. And he also asked himself how this transition happens, because he wasn't sure whether this transition comes from small vortices and then the vortices increases when the Reynolds number increase, or whether it at a critical value of the Reynolds number transition happens in a sudden way. So he was asking himself whether the flow experiences a subcritical or supercritical transition. In fact, the flow we are interested in, so the simple flows in some channels, I mean the pipe, so the circular section a pipe, or a rectangular section flow in a channel, or even this flow, the plane wet flow, is the flow between two walls that move in two opposite waves, so which is typical of cases in which we have the lubrication of mechanical parts. So these simple flows, which are called shear flows because they are characterized by a shear, by a gradient of velocity, these flows here experience all a subcritical transition. So it means that the transition to turbulence happens for values of the Reynolds number which are lower than the critical value of the Reynolds number, which comes from an instability, a linear instability analysis. We will see that later. And so in this region here, in this bifurcation diagram, we see the Reynolds number and the energy of a perturbation to the laminar state. So our laminar state is a steady solution. It does not move, it remains there. We do not have vortices. It's an equilibrium solution. And if we perturb it with the perturbation of very low energy, in this region here, the flow stays laminar. Okay, so this black line here is the line that separates the turbulent regime from the laminar regime. But in this region here, from this Reynolds number, this value of the Reynolds number, which is called the global Reynolds number, to this linear instability Reynolds number, transition depends on the energy of the perturbation itself. So if I have small energy in this region here and the Reynolds number close to this value here, the flow stays laminar. But if I increase the energy of the perturbation, the flow goes to turbulence. And we will be interested in this talk to compute this curve here. It is not easy to perturb because we are not talking about a simple dynamical system with 1, 2, 3, even 10 degrees of freedom. But since we're dealing with partial differential equations, our system is infinite dimensions. Then, of course, we will discretize the equation of a given grid, and we will have millions, even billions of degrees of freedom. So computing this curve here is not as easy as you can do that for a very small or ordinary differential equations. First, we are dealing with partial differential equation, and then we have three-dimensional flows in large domains. So it will be a huge computational task. And depending on when we are in this region here, so when transition depends on the amplitude of the perturbation, we can have different paths to transition. So this is the example of the flow on a flat plate, which can be a model for the flow, for example, on a wing, of an airplane wing. And we have always some perturbation that comes from the outside, for example, the turbulence, which is in the free stream. Okay, so outside this flow, which is created on the wing, for instance. And if this perturbation has very small amplitude, we can see the linear instability of the flow. So we will be here in this case. So the flow will experience linear instability, and then these structures within the flow will experience secondary instability, and then I have transition to turbulence. But if I am in this region here, even if I do not have linear instabilities, but if the perturbations are high within the flow, we see developing some structures that do not come from a linear instability of the flow. In fact, they come from non-normal mechanisms that I will explain you just later. And we have these structures that are called streaks because they are elongated in the stream's west direction, so the direction of the flow. And we have zones of low velocity and zones of positive high velocity, so the plus here, etc. And then these structures here, which are initially ordered, experience instability themselves, and the flow goes to turbulence. Or if we increase very much the perturbation amplitude, and we perturb directly within the flow, we can observe a transition which happens even before, so in a very small time. And so the transition to turbulence in this region here is very complicated because we are very paths to transition. And these paths are schematized here. They, of course, depend on the amplitude of the environmental disturbances that I have within flow. So as we said, for low amplitude, I have a linear instability, so modes that experience secondary instability and then goes to turbulence. And here in this region here, for moderate amplitudes, I have the non-modal mechanism inducing these streaks here. So this part, which is called transient growth, is referred to that, and we will see just in 1 minute what it is. And then we can just go to turbulence by perturbing non-linearly with a very high amplitude perturbation. And for the moment, we are interested in this part here, which is the one that is really at the edge of this bifurcation diagram. So we are really interested in this part here. And we said that this path to transition comes from a transient growth of the perturbation. It does not come from a linear instability, a linear asymptotic instability, but to a growth which is transient of the energy of perturbation. So let's consider at first our problem, which comes from the incompressible non-dimensional Navier-Stokes equation. So they're really the same set of equations that Olga Ladyzhenskaya used for many works. I will cite some of them later. And the flow is incompressible, so this is the incompressibility constraint. U is the velocity, and P is the pressure, so the velocity must be dimensionless free. And so here U is our instantaneous velocity, P is our instantaneous pressure. But I can, since I'm interested in the stability of initial steady flow, initial laminar flow, I can decompose this velocity here and also the pressure in a steady part, so in a part which is an equilibrium solution of this set of equations. So a solution which do not depend on time, so it's steady in time. So this derivative here will be 0, and a perturbation. So as I said, the base flow, it's a steady solution, so it will be governed by this set of equations here. And if I inject our decomposition of the perturbation in base flow and perturbation, so U prime will be the perturbation and capital U is the base flow, I will inject that in these equations, and I use this equation here, I obtain the perturbative Navier-Stokes equation. And since I am in this moment interested in linear mechanism, linear perturbation, I will say that this U prime is infinitesimal, and I will drop the nonlinear term. So here I directly wrote the equation in a perturbative form without the nonlinear term. So I must have a term U prime dot nabla U prime, and I've dropped it. So this is the linearized problem. These are the linearized Navier-Stokes equation. I linearize the Navier-Stokes equation around the base flow, which is a steady solution. And so I compactly write this linear problem in this form here. Here I forgot a prime, sorry. And then I said that my perturbations should be exponential in order to have a typical stability analysis. And I observed that all the modes are asymptotically decaying. So the flow is stable. We are really here in this region here. Okay, the flow is linearly stable. I'm not here, I'm here. So the flow is stable, but if my eigendirections are not normal between them, even if they hold decay, so here I take just two eigendirections and I say, okay, at a time equals 0, I have these two eigenmodes which combine and give me this vector here. These two eigenmodes decay in time. So they became, from the blue line here, I go to the red lines here. They both decay, but they decay with different rates, and they are non-orthogonal. The eigendirection are non-orthogonal. You can see that if I have the different decay rates and the eigendirection are non-orthogonal, I can have an increase of the perturbation at small times, at transient times. So the energy of the perturbation can increase. And this increase of energy is dangerous because they can induce, as we saw that, the energy of these streaks in this case can increase very much. And then when I have a perturbation of a very large energy, it can induce a secondary instability and transition to turbulence. Okay, so the structure we're interested in the first part of the talk comes from the non-normality of the linearized Navier-Stokes operator, which simply is due to the fact that the eigendirections are not orthogonal between them. It is a feature of all the flows we will consider. Okay, so how the researchers discovered that this normality of the Navier-Stokes operator was discovered in the 90s by means of an optimization of the energy. So some authors in the same time say, okay, which is the perturbation at the time 0 that gives me the maximum possible energy at a given target time. And they saw that, in fact, this maximum energy perturbation, so this optimal energy perturbation can increase its energy of several order of magnitude. And this typical mechanism here inducing this transient growth of energy is given by a mechanism which is called the lift-up mechanism that induces the streaks that we saw before. And the mechanism is very simple to explain. Imagine we put two vortices which rotate in an opposite way, so counter-rotating vortices within our initial flow. Our initial flow is a shear flow. What does it mean? It has velocity equal to 0 at the wall, because of course we have friction, so the flow must decelerate close to the wall, and it has an high velocity far from the wall. So this is the wall. This can be, for instance, the center of a channel, of the free stream, or whatever. And the vortices take the flow, which has a very low velocity from here, and put it up. And at the same time, they take the flow, which has very high velocity here, and they put it down. And so they create the streaks. So the one that we saw before, this one, streaks of negative and positive velocity, elongated in the stream-wise direction. So they simply transport the shear of the base flow, and they create these streaks of velocity. The problem is that these streaks of velocity increase their amplitude very much, and they became themselves asymptotically unstable. So we can do an instability of this flow, and we see that this flow with streaks is unstable. And you can see that the streaks become to oscillate, and then from the stream-wave vortices go to the streaks become unstable, and the instability recreates the stream-wave vortices. This is a cycle which has been called the self-sustained cycle, which sustains, in fact, turbulence in all the flow that we saw. And this same cycle sustains, gives us the existence of some relative attractors, which are the attractors that sustain turbulence themselves. So based on this cycle here of non-normality and then instability, we have several equilibrium solutions, traveling wave solutions, periodic solutions that sustain the turbulence. And in fact, Olga Ladyzhenskaya was the first to demonstrate the global existence of a stationary solution, so equilibrium solution to the Navier-Stokes equation, so really attractors of the Navier-Stokes equation. And starting from her, then there has been a lot of research of these equilibrium solutions. Some are very simple to compute, and so they can be computed analytically. But in the last 10 years, there has been much work trying to computing them by means of numerics. So all these states here have been computed numerically. And now there is a picture of the dynamics of this type of flows. So the subcritical flows that can stay laminar or goes turbulent depending on the amplitude on the energy of the perturbation, that I will show rapidly here. So we have a laminar solution that is stable. You can see here, so it's an equilibrium and it is stable. And then it is not the only attractor, relative attractor in our projection of the phase space. Of course, our phase space has infinite dimensions, so we cannot really see that, but it is a projection, just a picture of what we can see in reality. And we have other states that can be equilibrium states, traveling waves, or periodic orbits that are rather close to the laminar solution, and they're relative attractor. What does it mean? They have some eigendirections that are stable and some eigendirections that are unstable. So if I perturb it in this direction, the flow goes here, and if I perturb here, the flow goes in the equilibrium solution, etc. And these states that are called the edge states that are close to the laminar solution, they're stable manifolds, so the stable direction creates the separatrix of the basin of attraction of the laminar solution and one of the turbulent solution. So here, if I start my trajectory here, the flow goes to turbulence, and if I start my trajectory here, the flow goes back to the laminar solution. And this is our separatrix that comes from the stable directions of all these solutions here. These are called the edge solutions, and this is called the edge of chaos, or simply laminar turbulence separatrix. So they really separate the phase space. Of course, here I did a sketch, but we never can have the whole laminar turbulent separatrix. We can only compute some points, some particular points of this separatrix, and we will do that later. And so this is what we see close to the laminar solution. So for energies, so all these points, when I go, I start from the solution here, and when I go far from the solution, I increase the energy of perturbations, okay? So for low perturbation, I stay here, and for high perturbation, my dynamics became turbulent. So here I have turbulence, and these are all the equilibrium solution of periodic orbits that sustains turbulence, as I told you. And so the trajectory can go from one to the other, but in fact what it does, it never goes on one of these equilibrium, it goes close to one equilibrium solution on one periodic orbits along the stable direction, and then it gets repelled by it. And I mean, the trajectory walks close to one and then close to another and gets repelled. And we know that the dynamics when we go close to this solution here is the one that of the self-sustained process that I showed you before. So it's this dynamics here. But we still don't know very much what happens when we go far from this solution here. So we get repelled from these solutions. So in this talk, we will be interested in 2 points in this picture of our flow. So the first one is to compute one very important point of this laminar turbulent separatrix. The most important point of this separatrix will be the point of minimum energy, so the closest point in our projection of the phase space to the laminar solution. Because if I'm able to compute this energy here, so this point here, I'm sure that if I perturb the flow with a perturbation which has energy lower than this value here, I will for sure go back to the laminar solution and will never go to turbulence. So I can stay safe. My drag will never increase up to the values of a turbulent flow. So this is our safe region, and we can only compute it by having this point here. So what we will do, we will try to compute the perturbation of minimal energy in the laminar turbulent separatrix, and for doing that, this minimal energy perturbation should be the energy which experiences the largest possible growth for the minimal possible energy, and that stays close at large times, that is close to the laminar solution. So this perturbation must approach the edge state at a large time because it is on the laminar turbulent separatrix. And so this one is a stable manifold of these edge solutions here, and it must experience an optimal energy growth because it's the most dangerous one. So for doing that, I will use a nonlinear optimization coupled with the bisection of the initial energy, and I will explain better that in the next slides. And the second part of the talk will be linked to the dynamics of the turbulent flow itself. So I know what happens when I go close to these solutions here, to these coherent state, exact coherent states here, so the equilibrium that I told you before, but I really don't know what happens when I'm far from them. When I'm far from them, what happens, there are some events in the flow that have peaks of energy or dissipation. So within the flow, we can observe the self-sustained process that we already know. It's characterized by districts, but we also observe these high dissipation events that are called bursts or bursting events. These highly energetic and dissipative bursting events might be linked to a nonlinear optimal mechanism of growth of energy or dissipation in a similar way as the streaks that we saw before are linked to a linear mechanism of energy growth due to the linearized Navier-Stokes equation. So we use nonlinear optimization using the Navier-Stokes equations for answering to these 2 questions. So the first will be computing this point here, the point of minimal energy on the laminar turbulent separatrix, and the second one is characterizing the bursting event in which we have peaks of energy and dissipation in a turbulent flow. So for both of them, we need this nonlinear optimization that I saw before, and we will do that by using a Lagrange multipliers framework. So in the first part, our objective function, so the function that we want to optimize, is the energy, because the energy of the perturbation is a measure of the distance from the laminar solution of the perturbation itself. It's a L2 norm, so it's a measure of the distance from the optimization. So our objective function will be the integral kinetic energy of perturbation within the flow. So here we have the 3 components of velocity squared. So we take the square of the 3 components of velocity. We integrate in the 3-dimensional space. So we do an integral in the whole space. So we take the square of the perturbation in the whole domain. And this defines us the scalar product that we indicate with the brackets here. And we want to optimize this objective function at a given time t. We call it t or t opt, depending on the framework. And we want to optimize the energy of these perturbations because they are the most dangerous perturbations within our framework, constrained by the nonlinear Navier-Stokes equation. So our perturbation must respect the nonlinear incompressible Navier-Stokes equation. And we will enforce this constraint by using some Lagrange multipliers, which are called also adjoint variables. So this is our adjoint velocity, and this is our adjoint pressure. The adjoint velocity enforces the Navier-Stokes equation written in a perturbative form. And the adjoint pressure enforces the incompressibility constraint, so the fact that the perturbation is divergence free. And this terms here just sets the energy of perturbation. This constraint says that the energy of the perturbation, so this form here written from time 0, is equal to a value, which we call it 0, a given value. We want to optimize this function here, so we put its variation to 0. We must put its first variation to 0 with respect to all the variables. So by putting its variation to 0 with respect to the adjoint variables, so the Lagrange multipliers, we reobtain this equation here that I wrote here using the Einstein notation. So this is the divergence of u equal to 0, and these are the Navier-Stokes equations in a perturbative form. And this must be 0, of course. So I must respect the Navier-Stokes equation at all times. But if I put the first variation of the Lagrangian function to 0 with respect to the velocity and the pressure, I obtain a coupled set of equations, which is the adjoint set of equations of the Navier-Stokes equation. So these are the adjoint Navier-Stokes equations. This is the same incompressibility constraint on the adjoint velocity. And these are the adjoint counterpart of this equation here. And also the adjoint equation must be enforced at all times. Because why at all times? Because here I have an integral in time. This equation must be respected at all times because the flow should be realistic at all time. And then I have this equation here that comes from the first variation with respect to the velocity of time t at the target time, which allows me to switch from the velocity to the adjoint velocity at time t. And this is the gradient with respect to the initial velocity. So we want this gradient to go to 0 because I want to optimize with respect to the initial condition. But I cannot just say, okay, this is equal to 0. I have to iteratively put it to 0 by using a looping algorithm. So the looping algorithm is made as follows. So we choose an objective time and an initial guess. We integrate in time by means of a code, a numerical code. We integrate in time my Navier-Stokes equation from a time 0 to the time t. So we do a time integration of the equations up to time t. Then we use the equation that we see here in green that allows me to switch from the velocity of time t that I obtained by the Navier-Stokes equation integrated in time to this dagger velocity here, which is the adjoint velocity. And then I have this velocity at time t, but I need the one at time 0 for computing the gradient. How can I get this equation? By integrating in time the adjoint equation from time t to time 0, so backwards in time. So I integrate the adjoint equation from time t to time 0. And now I can obtain my gradient because I have this variable here and the one that comes from the initial guess before. And I can update the initial perturbation by using the information on the gradient. We use a gradient rotation algorithm, but we can use whatever algorithm made depending on the gradient. I have just to update the initial perturbation in the direction of the gradient. We use the gradient rotation because we also enforce the fact that the initial condition must be on the hypersphere at energy 0. And then I go back here iterating until I have convergence on the energy or the gradient goes very close to 0. And then we can do another optimization at another objective time. And just one thing to notice here, not only I have to integrate in time two sets of equation in a three-dimensional flow, so millions of we can potentially have millions of degrees of freedoms depending on the domain considered, but we also have to store the velocity of each time. Why? Because the adjoint equation here have the velocity at all times here as a convection term. So it's a computationally huge problem. So since it is a computationally huge problem, we consider a simple flow. So the flow in a rectangular duct. And so in fact, these two flat plates are infinite for simplicity, and we use periodic condition in the streamwise and in the spanwise direction. So in this direction, and the flow is driven by a constant pressure gradient. So we can have the laminar solution, which is the plane quasi solution, or we can have turbulent conditions. And we use an open source code developed by Gibson, which is called channel flow, and it uses a spatial discretization based on Fourier, Chebyshev, and Fourier discretization. And for the first computation, we choose a small domain, so we have a small grid, but you will see that later that we increase very much the domain. And so the degrees of freedoms will be much higher. So the first problem we're interested in is the computation of the perturbation that are close to the laminar solution and can go to turbulence with minimal energy. So we start doing many nonlinear optimization for different values of the energy and the target time. And for very low energy, we obtain a perturbation which is equal to the ones that I can compute by a linearized mechanism. So the linearly optimal perturbation, we saw that before, is the one linked to the Lifta mechanism that I explained you before. These are simply streamwise vortices. So these are isocontours of vorticity. So I have a vortex that goes like this, another that goes like this, and there's exactly the same as the linear optimal perturbation. And when I increase the energy, the vortices, the perturbations start to localize, the vortices become smaller and becomes inclined. So that's an indication that the nonlinear mechanism come in. So I'm really going close to the laminar turbulence separatrix. I'm not here close to the laminar state. I'm going a little bit higher in the phase space. And then I have much localization and much inclination, and I start to go close from the laminar turbulence separatrix. And so I need an energy that it's, that do not go to turbulence and do not go back to the laminar state. Here you can see it's a sketch of the energy with respect to time. So I have to, for computing my perturbation, which stays on the laminar turbulent boundary, I have to start with a low energy and be able to compute a solution, an optimal perturbation that increases their energy optimally, but it has an initial energy so low that it cannot go to turbulence. So it goes back anyway to the laminar solution, to the laminar state. And then I need an energy which is a little bit higher, so that it is on the other side of the laminar turbulence separatrix. And so the energy increases and goes to turbulence here. And then I have to bisect my energy. Each time I optimize, so I compute the most dangerous perturbation, the one with the most growth, the largest growth at a given time. I optimize, and I see, okay, does it go to turbulence? I have to decrease my energy. Does it stay laminar? I have to increase my energy for getting really the threshold energy that stays on the laminar turbulence separatrix. So I need optimization and a bisection of the value of the initial energy. And I need a large target time in order to avoid initial transient link just to linear mechanism. So I need to consider a large time for which really here I observe turbulence, and here I stay close to the one that we called edge states. Okay, so in this way, by optimization, every time I use my optimization in order to compute the most dangerous perturbation, and then I bisect the energy between the two values, the two last values, the last value that induces turbulence and the last that induces laminar flow. And in this way, I compute the minimal seed. Minimal seed is the disturbance of minimal energy that asymptotically approaches the laminar turbulent attractors. So this is just a sketch. So if I take a time which is low, I can go to local minimum of the of our laminar turbulent boundary. So this will be this blue point here, and it goes to the edge, it goes to turbulence, but it goes there with a lower time. So for not computing local minimum, I need a very large time. Okay, so let's see what happens if I start with a high value of the energy and I do my optimization for a time. In this case, the target time is 200. I compute a perturbation that goes to turbulence. So this is a turbulent seed, the one in purple. Then I decrease very much my energy and I compute a laminar seed. So the flow goes back to laminar. So this is the energy of perturbation in time. So I can see that the energy goes to zero. My flow goes to the laminar. Of course, here I have a linear perturbation that is close to the one that, I mean, it's not linear because I compute it with a non-linear optimization, but it's close to the linear ones because the energy is very low. And then I bisect the value of these two energies here. I take an energy which is in between, and now I obtain a turbulent seed. And I bisect again from this turbulent seed to the laminar seed that I computed before, and I obtain a laminar seed. Then I bisect again, and I obtain this curve here in which I start to see this part in which I really see that the perturbation approaches what is called the edge state, the relative attractors on the laminar turbulence particles. So this is a good approximation of my minimal seed, and the minimal seed is made like this. So here I see the vorticity in green and the low velocity regions in blue. So I have some vortices which are a little bit inclined and localized, so close to the ones that I saw before. And this is my minimal seed for the very small channel that I considered. And I can show you just the dynamics if you're interested in. I go out just one moment. So this is what comes for the integration in times of my equations. So you can see that in the first part of the video, I have just some streaks that are oscillates weakly, and then here I have turbulence. So when you observe the streaks, I'm close to this part here. So I'm close to the edge solution for the attractor in the laminar turbulence separatrix. Okay, so we do that in a very small channel, so in a very small domain. What happens? The first one thing about what happens if I do that at different Reynolds number, because we did this computation for just one value of the Reynolds number, but we said that we were interested in a bifurcation diagram. Bifurcation diagram is Reynolds number with respect to initial energy. So I want to know the curve of minimal energy for which I'm sure that if I below this curve, the flow will never go to turbulence. And by doing the same at different Reynolds numbers, I obtain for a sufficiently high Reynolds number. So you can observe that this point is out of the scaling because it's very low, it's very close to the Reynolds number for which I do not have transition. I cannot have transition. So the global Reynolds number, if you remember before. But for a sufficiently high Reynolds number, the minimal energy for observing transition collapse on this curve here. This is a logarithmic scale, so the scaling here is exponential. So I have an Reynolds number at the -3.2. So I'm sure that if I'm here, I will never, my flow will never goes to turbulence. If I'm over there, my flow might go to turbulence if I have a sufficiently high energy of the perturbations. And if I compare this threshold here with the threshold, minimal energy threshold that were reported in the literature before for shapes of perturbation that were fixed, so Here, for instance, it was used the linear instability mode. Here we use a couple of streamwise vortices. I mean, people fix the shape and then do the bisection without the optimization, without the nonlinear optimization. So they might never be sure that they were the most dangerous perturbations in the flow. And you can see that all the scaling reported in the literature are higher. So all the minimal energy would much higher, 1 order of magnitude even higher, or more order of magnitude higher than the value we computed. And we did that also for other flows, for instance, the boundary layer flows that I showed you before. And we observed the same. Our scaling, which is really the safe regions, we really said the safe region is many order of magnitudes lower depending on the other scalings reported. And in this region here, people might be, before this works, might say, okay, I'm safe, I cannot have transition. But if you perturb with minimal seed or with a perturbation that are close to the minimal seed, you might, in fact, have transition here. So the scaling in the literature were not sufficiently accurate. If we want to have an accurate scale, an accurate threshold energy, an accurate bifurcation diagram, we have to use nonlinear optimization. We said that we did that for a very small domain. In a very small domain, when turbulence happens, it happens everywhere. So we have global turbulence. The flow is fully developed. We do not have regions in which we have turbulence and other which have the laminar flow. So when the turbulence happens, it fills the whole domain. But for some values of the Reynolds number in a very large domain, we can have sub-regimes in which the turbulence is localized. So for instance, in the flows we're interested in, so the channel flow, and also other flows like the Couette flow, the one that I told you before is important for lubrication, etc. We have these regimes of localized turbulence in which we have sustained regions of turbulent flow within a laminar flow. And these regions are strange because it is observed that they happen in an inclined, they have an inclination with respect to the direction of the flow. So this is the streamwave direction, and you can see that these turbulent regions are inclined. So turbulence is localized in space, and it does not fill the whole domain. So our question is, do the scaling that we have found computing the minimal seed changes when the turbulence changes from fully developed, so spread in the whole domain, to localized? In fact, the minimal threshold, so the bifurcation diagram, changes very much. So this is the scaling that we saw before, the Reynolds number at minus 3.2. If we increase very much the domain, so before we have 2 pi times 2 times pi, and now we have 2050, so we have increased it orders of magnitude. So if we increase very much the domain and redo the same optimization, of course, here the problem is huge because for each optimization we have, you can see here we have 10 to the 7 points. We do the same for different Reynolds number, and not only we have much lower minimal energy values, but we have also a different scaling. So the scaling is minus 8.5, at least within this region in which we might have localized turbulence. Then we are not sure what happens here if we go back to this scaling here, because then we will have a Reynolds number at which the turbulence will be spread in the whole domain. But at least for this range of Reynolds number in which the turbulence is made like this scaling is different, and the minimal structure changes as well. So why it changes? Here we see the whole domain, and this yellow part here is what we see before. It's the minimal seed. But we do not focus on this part here that is very similar to what we see in the small domain. We focus on what we have in the outside of this small region here. If we integrate in the nonlinear, in the wall normal direction, the flow. So here we're looking at the channel flow from above. So we are looking at the vortex. So this is the streamwise direction, and this is the transverse direction. So the direction normal to the wall will be comes out from the screen. And so if we integrate the flow in the wall normal direction, we observe large-scale vortices. We observe large-scale vortices that transport in time this perturbation. And so the fact that the scaling is different and the minimal threshold energy is different comes from the fact that we do not only have this part here, but we also have these quadrupolar large-scale vortices that, I mean, we cannot have in a small domain. So the domain that we had before, it was, I mean, like this. So we couldn't observe these vortices. And these large-scale vortices have, I skip just for a moment these large-scale vortices have the role of transporting the minimal seed along one preferential direction here, because you can see that when they rotate, they transport the perturbation here and here and here and here, and they create the turbulent, inclined turbulent bands that are that sustain the turbulence in this range of Reynolds number. So we start from this minimal seed here, and with the quadrupolar large-scale vertical structure that I showed you before, and we induce a first band, a first inclined turbulent band, and then this band interact with itself and then interact with the other bands, and then it creates turbulence like this, immersed in laminar. So the white parts here are laminar and the yellow parts are turbulent. So we have the laminar turbulent pattern that I showed you before. And we can also see that the structure of the minimal seed changes depending on the Reynolds number. So for this Reynolds number here, that is for which the turbulence starts to become more extended in space, this structure here is close to the one that we saw in the small domain. So we have vortices, inclined vortices, one in blue and red, and we have regions of low velocity, the one in gray. But when the Reynolds number is the one for which the turbulence is not spread in the whole domain, is localized in space, we have a very different structure. So not only we have computed the scaling for a small domain, but we have demonstrated that this scaling here must be recovered in a sufficiently large domain, at least when we have a spatial-temporal dynamics of turbulence, which is complex. So when we have patterns, spatial-temporal patterns of turbulence within a laminar flow. Okay, so I don't have much time, but I think I can talk 5 minutes about the part of investigating what happens in the, I will skip this part here, sorry, and I will go straight to the last slides. Okay, so I told you before that the focus were two. The first one was to compute the minimal threshold for transition. The second one was trying to use this nonlinear optimization for explaining what happens during the events that induce peaks of dissipation and energy within an already turbulent flow. Because why we're interested in that? Because if I have peaks of dissipation, so the dissipation increases of orders of magnitude, even if a small part of the domain, I increase the drag very much. So I'm interested in understanding what happens in these regions here for trying to hindering this mechanism. And some recent works have shown by using a conditional proper orthogonal decomposition. So they take in a simulation the 1% most dissipative structures within the flow, and they decompose it in a normal base that provides the most energetically structures within the base, within the flow. And they saw that the structure are given by this typical hairpin shape, so really the shape of an hairpin, the one that kids put in the hair, and they're not linked at all with the self-sustained process. So it must be a different mechanism. Can this mechanism be linked to an optimal growth, a quasi-optimal growth of the dissipation in a fluid? So for doing that, we use our nonlinear optimization to optimize this time the integral turbulent dissipation, which is given by the double scalar product of the gradient of the fluctuations here, in integrating in the volume, so in the whole domain, and also in time, from an initial given time t0 to t0 plus t. Okay, so this is the same role of the target time we saw before. And now we perturb a turbulent flow. So we want to compute the perturbation, this one, that once superposed to an already understood turbulent flow provides this perturbed velocity here. So we would like to optimize the dissipation in the whole flow, constrained by the Navier-Stokes equation written on the perturbed variables, of course. So here we have again the Lagrange multipliers here, and the same constraint on the initial energy, and the equation are nonlinear and written on the perturbed turbulence snapshot. We use the same set of equation as before, but we have a difference because we have, in the adjoint equation, we have a term here that comes from the fact that we are integrating, we are optimizing the dissipation and not the energy, and the dissipation is integrated in time here. So we have a forcing here at each time, but the mechanism is the same. I have a direct adjoint looping, so I integrate the Navier-Stokes equation, then I use the X condition here to obtain you the adjoint velocity, and then I integrate the adjoint equation backwards, and then I update in the direction of the gradient the initial perturbation. So using the same algorithm, I obtain this initial perturbation, that is one that induces an optimal growth of the dissipation within the turbulent flow. I can observe these are perturbation of the streamwise velocity, so the perturbation in the direction of the flow. And we can see that we have a typical inclination here. We will see later what it is linked to. But before doing that, we can look at the evolution of the flow. So the black curve here is the kinetic energy of the undisturbed flow. So we integrate in time the Navier-Stokes direction, the Navier-Stokes equation without perturbing, and we have some turbulent fluctuation, but we stay close to a steady, statistically steady value. And the green line is the one from our optimized perturbation, from our optimized simulation. So we can see a peak, a very high peak of the energy, and a very high peak of the dissipation. Epsilon is the dissipation. And we did that for different realizations. So starting from different initial turbulent snapshot, and we have the same peak. So of course, our perturbation is able to create peaks of dissipation. What happens between the flow, in the flow? So these are the values of the dissipation in the flow seen from above. So I'm seeing here the streamlines and the transverse direction. And very low values indicate that I have dissipation which is close to the mean value, so it's very low. And high, the yellow parts are the regions in which I have the peaks of dissipation. This is the unperturbed flow, and this is the flow that I optimally perturb by this perturbation. And I can see I induce in the whole flow regions of high dissipation. When I do that, I perturb everywhere. If I look at the trajectory of the flow in a projection of the phase space in the kinetic energy and dissipation, I see really a burst of dissipation and kinetic energy. So I really increase very much my dissipation. But I mean, this situation is not very realistically, because usually in a real flow, these events of high dissipation happen in a local region. So I take my perturbation here and I clipped in one part. So you can see it here. I do a clipping in the streamwise and spanwise directions, and I perturb it all locally. You can see that here I obtain these peaks of dissipation, which are only in a local region. And if I look here at my trajectory, it stays close to the trajectory of the undisturbed flow. So the gray line is the trajectory, is the typical turbulent trajectory and the undisturbed flow. And the black line here, I don't know if you can see it well, is the one coming from this case here, the locally perturbed flow. So I stay in the region of the turbulence, but I induce local peaks. How can I see that I induce local peaks of dissipation? So I'm inducing a high dissipation events. I compute, using various realization of my optimization, I compute the probability density function of turbulent dissipation. When I have my high dissipation events, my extreme events, I have an heavier tail in the probability density function of the dissipation. So here I have a dissipation which is, for instance, 25 times the standard deviation of the dissipation itself. So the dissipation is much higher. And the red line and the dashed line are from an undisturbed realization and from a simulation which are perturbed not optimally, and they are similar. But when I perturb optimally with my global optimal, I obtain a tail of the PDF of the dissipation which increases. So here I can induce, and I have a probability of inducing very much high dissipation events which increases. And this is true also if I perturb only locally the flow. So really my perturbation is able to induce high dissipation events also locally. And how it creates these high dissipation events, because we're interested in explaining the occurrence of these events. If we superpose our perturbation, so the gray, the shaded contours here, on our initial turbulent snapshot, which has been filtered in order to pass only the large scales, so the scales linked to the streaks. Remember the streaks we saw in the beginning, the one that were elongated in the streamline direction. We can see that the perturbation, the optimal perturbation, goes really in the region of interaction of inclined streaks here. So this explains the inclination that we saw before. So the optimally dissipative perturbation that we compute, it really comes from a streak instability mechanism. So it put itself at the region of interaction of a positive to a negative streak. So the solid line is a positive streak and the dashed line is a negative streak. And in this way, it increases, this streak instability increases the dissipation very much. And this is true also if we do that only locally. And the last thing that I will tell you, okay, we computed this optimal perturbation, but how do we know that these events that high dissipation events that we induce in the flow are similar to the realistic ones, to the one that they occur? In order to understand if we are computing something that has a realistic sense, we compare our optimal perturbation with the conditional proper orthogonal decomposition, which have been made by some years ago by Hackenschmidt, the one the harping structure that I showed you before. Here we see just a section of the flow. So this is the transverse direction, and this is the wall normal direction. This is what is found by conditional proper orthogonal decomposition. So in the DNS, we take only the high dissipation events that occurs naturally. We decompose in orthogonal modes, and we take the more energetic. We obtain this, and we do in our optimal perturbation, and we obtain that. So they're basically identical, and the same is observed in different directions. So if we take the streamwise direction with respect to the normal, etc. Yes. So yeah, okay. So I conclude by saying that this optimization is able really to capture what happens in a realistic flow. And I conclude here. I skipped the conclusion. It was finished. And so if you have questions, please let me know. Thank you. Sorry for being long.
I think if we have time just for a very brief question, if any. Okay, there are no questions in the audience. Just a very brief question from me. You have explained a model of turbulence which consists in your system visiting several unstable objects. Do you think that this covers all possible turbulence, or there are examples in which this cannot be a good explanation?
So example in which the picture of turbulence is not
as easy as this. As just
not as this.
The system visiting different unstable objects?
Yeah, in the case we consider, I mean, in the simple flows like the flow on a channel, etc., we observe, I mean, the turbulence is really sustained by this unstable object. But you can say, okay, how these objects which are unstable can sustain turbulence, because they always have many stable directions. So so the trajectory is comes close to these objects along the stable direction, and then usually the unstable direction are very few. So typically the ones that are in the laminar turbulent boundaries have only one unstable direction. So of course they are relevant. These periodic orbits equilibrium are very relevant to the flow because they have many stable directions. Okay. Okay, thank you. Bye. Bye.
Okay, so in the meantime, let me start introducing Giuseppe Mingione, or Rosario Mingione, because everybody calls him Rosario. He's an Italian mathematician, professor at the University of Parma. He did his PhD in Napoli with Nicola Fusco, and he obtained the PhD in 1999. So he's quite young. And right, well, younger than me, for instance, 5 years younger. His topic of research, his area is partial differential equations and calculus of variations, and more particularly regularity theory and nonlinear potential theory for elliptic and parabolic problems. Regularity theory, he has important words about partial regularity, when a solution is not regular everywhere, but maybe it's regular in sets, in big sets, determine these sets, right? And this connects his work with those of Almgren, De Giorgi, Morrey, Giusti, very important. And then more recently, he has been working rather in nonlinear potential theory, and this is like an extension to nonlinear equations of the classical potential theory from harmonic analysis, Green's functions, this kind of estimates, right? And it's a very powerful tool for which he's probably one of the top researchers in the world, and he considered quasi-linear equations, other degenerate equations, and more recently he has very important works on non-local operators also, in nonlinear potential theory for non-local operators, something that many people, in particular the group in Barcelona, we are interested about. So said this, he has got a good number of awards: Bartolozzi Prize, Stampacchia Medal, Cacciopoli Prize, Amerio Prize, and he has had an ERC grant in 2000. He had an ERC grant, Consolidator maybe, or Advance.
At that time, Consolidator didn't exist.
I see.
Yeah.
2007. And then he was invited speaker at the 2016 ECM in Berlin, and he is 2017 Commander of the Order of Merit of the Italian Republic, given to him by the President of La Repubblica, right? So, and then there is one thing that I don't like in your CV.
Only one.
Only one. Yeah. Is that you have a lot of citations, okay? You have double than I have, okay? And that's this is really impressive. He has 8,300 citations in Math.net. You also have the double of publications that I have, but but that he has a lot of citations, and therefore he's been something very difficult to achieve. That is a Web of Science highly cited researcher for 9 editions since 2014. All right, so he's a very important mathematician, as you see, and he will talk to us today about work he has done, and that is related to work of Olga Ladyzhenskaya on elliptic and parabolic equations. So here the names are Hoff, Cacciopoli, and Schauder, reloaded. So I said some names. Let me ask you something. I said Angrem, De Giorgi, Morey, Justi, connected to your work on partial regularity, for instance. What would be the names connected to potential estimates, which is nonlinear estimates? These names, for instance?
No.
Which
no.
one?
These are newer estimates because essentially it's a new field. There are no classical names, but the ones of Kilpelainen, Malit, Udinger, and Wong. And these ones, right?
Thank you.
Okay, thank you.
Thanks for accepting.
So thank you for inviting me. It's a great honor to come here and to celebrate Olga Ladyzhenskaya, one of my math heroes. And where's the
I have one.
okay. And okay, why Olga Ladyzhenskaya is so important? There are several reasons why she's so important, but she was one of the pioneers of something that we give for granted nowadays, but that was not at the time. That is a nonlinear approach to PDEs. So Ladyzhenskaya in the 50s, together with the Russian school in St. Petersburg and some other pioneers scattered around the world like Nirenberg, De Giorgi, Nash, and these people were pioneering nonlinear theory of PDEs. So sometimes they were dealing with linear PDEs, but their methods were genuinely nonlinear. And this was a completely different world that was just opening at that time. And those were the times where, the kings were linear PDEs. So the micro-local analysis in the style of Goding, Hormander, and then Bonny. And this was the dominating world at that time, because everything was done via fundamental solutions, explicit computations, and then fundamental solutions led to micro-local analysis that was really an empire at that time. But these more synthetic methods like the nonlinear methods that we are used to do these days, pioneered by these people and then by Moser, those were really something that were very, very rare to do, and because playing with nonlinearity means really going at the core of the phenomenon, because you escape all this classical stuff doing using linearity like fundamental solutions, parametrices, and so forth. This was probably one of the reasons that these people at that time, like De Giorgi, Nash, Morey, were not awarded with major prizes like Fields medals. They were just too avant-garde for that time. That Fields medal went to people like Hormander, that were of course like giants, but this means a lot about this and in the Western world, the pioneers were these people, and in Europe, for instance, Jacques-Louis Lyons and the school of Jacques-Louis Lyons. And in the West, in Russia, there was Ladyzhenskaya and her school, with other people, important people like Mazia, for instance, and Olienik and other people. Okay, so I'm going to talk about Ladyzhenskaya. So I have very good memories of my friends, of my Russian friends. This is a picture of myself and together with Olga Ladyzhenskaya at that time in St. Petersburg. And these are Grigory Seryegin and Nina Uyaltseva, two very strong mathematicians. And this is Nina Uyaltseva's place, and she cooked up for us, and she was an excellent cooker. And this is a famous, legendary monograph by Ladyzhenskaya and Uyaltseva that this is the unachievable 73 untranslated edition, Russian edition, that contains the proof, Nina Uyaltseva proof of the regularity of the P-Laplacian. That for the first time, that the one that Uhlenbeck then did for the vectorial case. And this is by Uhlenbeck herself, credited as the best paper of Uhlenbeck. And this is a pic credited to Neil Trudinger that can be found around, and these are Olga Ladyzhenskaya, Nina Uyaltseva, and Nina Ivochkina. This is another pioneer of non-uniformly elliptic equations and Monge-Ampere equations. And of course, there's a strong tie with the Italian school and and with people like Cacciopoli, De Giorgi, and so forth. I will skip this to be faster, and I will go at the core of my talk that contains some of my most recent results, but you will see that they are connected, strongly connected with Ladyzhenskaya. We will see now. Okay, what I'm going to talk about is minimization problems for integral functionals of the calculus of variations, and for solutions to non-uniformly, to elliptic equations in divergence form that are the most classical and natural equations that you can get, because are those for mathematical physics, are really those for mathematical physics. And the catch is given by the Euler-Lagrange equation, which is usually called the first variation of the functional. Usually you do what you do in basic calculus, you take the derivative of the function and you put it equal to 0 to find critical points, and this you can do also in function spaces, and you get the Euler-Lagrange equation. Okay, what is ellipticity? Ellipticity is that these derivatives, so A is a vector field, so this is a matrix. So the lowest eigenvalue at each point is positive, and this is just a way to bound the lowest and the highest eigenvalues of the matrix at each point. So ellipticity means that this is positively defined. So you never go beyond 0, so you are dealing with an energy. You are dealing with energies, and these are the two eigenvalues, G1 and G2. So this is the most general definition. Okay, I will not go into these very sophisticated classifications of ellipticity in Petrowski style and so forth. But for us, ellipticity is just that the lowest eigenvalues is positive, and then we get a bound on a lower bound and an upper bound on the lowest and highest eigenvalues. This is the easiest definition we can give at this stage, but this is okay for us. Okay, uniform ellipticity means that this quantity is uniformly bounded. Actually, there are several definitions in the literature. One definition claims that this is bounded for large values of z, those are really counting for us. But actually, you can take the sup, and that's it. So you can get the sup on every z. So why this is important? Because actually, this is the crucial quantity that you always encounter when you do any estimate. The ratio between the highest and the lowest eigenvalue is crucial. So in the uniformly elliptic regime, which is the classical regime, this is bounded, and when this is bounded, if this is bounded, you just keep it. You skip its existence and you just control it with a universal constant, and you don't care about it. And this is why. So this condition has nothing to do to be non-degenerate. You can be uniformly elliptic and being degenerate. For instance, the P-Laplacian operator, which is something that Nina Uyaltseva proved to be a regularizing equation, and that was studied initially by this is a theory that was really happening in Russia, because how Nina Uyaltseva came to this. Because, okay, technically speaking, she had the strength because she was developing the Giorgi's idea together with Ladyzhenskaya, and they were the first ones, Ladyzhenskaya and Uyaltseva, to recognize that the heart of the Giorgi-Nash-Moser theory was nonlinear. That is, that was developed for linear equations, but they discovered that everything went on for nonlinear equations, and they developed a lot. I was actually at Mittaglöffler in the fall of 2000s, and there was a common room. There were three people. Me, there was an irrelevant young guy, and then Uyaltseva and Reshetniak. And Reshetniak and Uyaltseva recalled how they came, because it was after a talk of mine talking about P-Laplacian. And then Reshetniak and Uyaltseva recalled how this problem was born. This was coming from quasi-conformal mappings when P is equal to n, and then Reshetniak proposed to Uyaltseva, and Uyaltseva solved the situation. These were, real strong people, and that they were not playing with definitions. They were playing with objects, with real objects. So why the P-Laplacian operator works? Because the behavior of the two eigenvalues is always the same. So the ratio is bounded, and this is ultimately, if you look at the proofs, so this is not transparent from the proof, but this is ultimately the way the P-Laplacian operator works. It can be degenerate, but the ratio between the two eigenvalues is always bounded from below and from above, so there's no problem. So you can do a lot of linearization here. Okay. And of course, this doesn't mean that you have to P Laplacian. For instance, you can consider more general nonlinearities. So the P Laplacian is a perturbation of the Laplacian via a nonlinear function. You can put a nonlinear function here, and this tells you that the ratio between the highest and the lowest eigenvalue is bounded. For instance, in the case of the P Laplacian, this is noted by P minus 2. And this has been done at length in the literature. So the literature is a lot about uniformly elliptic problems. Okay, the literature we know today, and Schauder estimates has also been treated, because Schauder estimates in the classical uniformly elliptic setting are a classical perturbation theory object. So you make perturbation around a good object. That's Schauder theory. So let me anticipate that in the non-uniformly elliptic world, this is not true anymore. So Schauder estimates are not perturbative, and that's why I found this to be interesting together with other people. So non-uniform ellipticity. So when you are not uniform, So if the ratio blows up at just one point, so you are not able to control this ratio, or at infinity, or whenever you like, then you are in presence of a non-uniformly elliptic operator. We may argue at one point, almost every point. No, because in this setting, the dependence on x is always continuous. So one point is like many points, positive points. So if at one point you are not able to control this ratio, then you are in the non-uniformly elliptic regime. And of course, you can give the same definitions for equations in non-divergence form or whatever you like. The essence is always the same. This ratio is not bounded anymore. It's not ensured to be bounded anymore. This is a classical topic. This is a classical topic because minimal surfaces operators are non-uniformly elliptic. They were first studied by Fing and other people, and of course by Douglas and Alphus. But then there's an extensive classical literature that has been a bit forgotten over the years. Why? Because this is a cultural fact. So why the Georgi-Nash-Moser theory is called in this way? Because De Giorgi and Nash proved it. Okay. Then the proofs were so difficult that people didn't understand because these were the pioneering days. So the only people who understood those are Moser, who found another proof, and in fact Moser was willing to get an easier proof, ending up actually with a more delicate proof. And Ladyzhenskaya and due altri. Yeah, but Nirenberg, but this was a small, but Nirenberg didn't work directly on it. But this was a small circle. But you see, already if you go outside this, it was difficult. And then we had to wait for people like Caffarelli and Di Benedetto to discover in full strength the ideas of De Giorgi. But essentially, this is why some people just kept this apart. I mean, okay, but nevertheless, Gilbert, for instance, Schrödinger's thesis is on non-uniformly elliptic problems, and then there was a lot of fine work to be rediscovered in St. Petersburg. In fact, many people in the West then rediscovered the people of the work of people in St. Petersburg without knowing it. Amongst them, Ivochkin, Skolkov, and Ivanov, especially Ivanov. But of course, there are important contributions by Hartmann and Stampacchia, by Serin. There's a big classical paper, and by Leon Simon. These are classics after the 80s, and I would like to outline the contributions of Zhikov. Zhikov was really a genius, but was an underrated genius. And if you look at Zhikov's papers, you will find Zhikov, Kozlov, Olienik. People nowadays top people are rediscovering, for instance, in homogenizations results done in the 70s by these people. This happens because often people know about problems by listening to them by other people. But you should not forget that one should also study by himself. So one should discover things. And we also have with Daletova and Ivanov, and especially Marcellini, who studied these things in the framework of the calculus of variations. This is a landmark paper of heavy reading, hard reading. by Ladyzhenskaya and Uraltseva, where they extend several estimates also by De Giorgi, Bombieri, and Miranda to a general setting of operators linked to minimal surfaces equations via different methods. So the full art of Ladyzhenskaya and Uraltseva is in this paper. Of course, there's a whole list of papers in the 60s about Ladyzhenskaya and Uraltseva. These are two classics by Neil Trudinger in different directions, more towards where the nonlinearity depends on the coefficients. And this is another hard-reading paper, a deep paper by Leon Simon, where you see this is the famous Michael and Simon inequality, which is essentially the isoparametric inequality of manifolds, and he uses this to develop a more general regularity theory and for non-uniformly elliptic problems. This develops and extends the previous paper by Ladyzhenskaya and Uraltseva. Okay. So what I'm going to talk about essentially deals with regularity of minimizers of the calculus of variations, and the emphasis today is on the presence of x. Usually the presence of x is underlooked because it's considered to be a perturbation, but this is not essentially this is essentially false in the non-uniformly elliptic setting. Let's see why. Okay, so this is, I'm just recalling here the definition of non-uniform ellipticity. And okay, so what is standard in the literature? You are in these situations. For instance, you want to prove that the gradient is bounded. Why? Because once the gradient is bounded, you in some sense can go back to the uniformly elliptic case because then the ratio stays bounded automatically in many situations. Of course, if you use that this is, typically you use that this is bounded to prove that the gradient is bounded. But now this is not bounded. So there's a competition. If the gradient is large and this grows too much, then you could end up with irregular minimizers. And in fact, if you look at the literature, in any possible condition, the main assumption in this setting is that this ratio grows as a small power of the gradient. Because if the power is too large, then this competition resolves in favor of irregularity. So that is the problem. So okay, of course, every author has his own definitions, and everything eventually boils down to assume something like this. And in the setting of polynomial non-uniform ellipticity, where you assume that the lowest eigenvalue grows like p and the highest grows like q, then these are called pq growth conditions usually. Then this grows as a difference, and of course you want to assume that q is not too far apart from p. These are called Marcellini's PQ growth conditions because Marcellini was one of the first was actually the first to introduce this condition and to study it systematically. So in the framework of polynomial non-uniform ellipticity, this is the thing you have to look at. And of course, also if you look at the Russian literature, there are the similar conditions. And if you look at Marcellini's papers, then these are the first examples of local estimates. Okay, a model condition is the following. You get a functional that grows like p and q, and these are relevant also in linear elasticity, for instance. And the condition that you find in the model literature is this one. So q cannot be too much far apart from this, depending on n. Otherwise, there are counterexamples. And counterexamples are given by Jacquint and Marcellini. But essentially, this is the same thing that you look in the Russian literature if you look at the papers by all the other authors, because that cannot be different. And there is still, in the autonomous case, there is still a lot of research on this because, for instance, there are recently interesting papers by Bell and Schaeffner. By Schaeffner, Hirsch and Schaeffner, they find the best possible bound to get that u is in L infinity. The best possible bound to get that u is in L infinity is not known in the autonomous case, but this is, and then there are recent papers by De Filippis, Christensen, and Koch. But this just is giving you a flavor of the kind of results that people are still getting these days. Okay. Now, the point is that in the non-autonomous case, we have the classical ratio. So you freeze a point, and then you get the ratio. On the other hand, you could also do another thing. You could find a ball and get the sup of the highest eigenvalue here over the inf on the ball. This is what we call a non-local ellipticity ratio that was introduced by De Filippis and myself in a recent paper. So usually this is non-local, so this is larger than the pointwise setting. This is bound to detect milder forms of non-uniform ellipticity. So is this artificial or not? Let's see. So this is the classification we give in this paper. We call that an integral is non-uniformly elliptic in the usual sense if it is in the usual sense for at least one point. It's softly if it's uniformly elliptic in the usual sense, and then the larger quantity blows up. And then it's uniformly elliptic if the larger quantity is bounded. So you see, if there is no dependence on x, all these quantities collide. So there's no difference. So what we do, we introduce an intermediate notion of non-uniform ellipticity. So of course you might wonder if this is just for getting just another definition. It is not. Why? Okay, let me consider this functional that was hidden in a paper by Zhikov. So it is amazing how people overlooked these papers. So so freeze x. If you are in a situation where a of x is 0, then this goes like p. Otherwise, this goes like q, but moderated, calibrated with a. So globally, Zhikov was interested in this because, for instance, if you have a composite of two different materials, two materials have two different hardenings. So usually in homogenization, you describe, for instance, an energy, you describe the anisotropicity of a material, putting a coefficient, and then doing something like this, for instance. So the anisotropicity of the material is this in the points. But this is not a strong anisotropicity, because it's essentially the material is qualified by its hardening exponent. Here you move the hardening exponent, describing a composite of a material where in some regions you get a P, in some regions you get Q. And this simple structure raises a surprisingly rich theory. So is this uniformly elliptic or not? In the classical sense, it is. So if you freeze x, this is perfectly uniformly elliptic. And so if you are in the uniformly elliptic setting, everything should be okay. But is softly non-uniformly elliptic. Because if you pick a point where there are two materials, then you get a soft form of non-uniformly elliptic. So if you look at the standard literature, this is considered to be uniformly elliptic. It is not under our new definition. So being uniformly elliptic in the classical sense means that everything around perturbation in uniformly elliptic problems should be okay. So what are the two basic perturbation theories in uniformly elliptic problems? Calderon-Zygmunt theory and Schauder theory. So Calderon-Zygmunt and Schauder should be okay for this kind of functionals. So anytime you get a Hilder coefficient, you should get a Hilder continuous gradient. This is not the case. This is a disturbing counterexample to regularity, telling that in the scalar K, you get a convex, uniformly strictly convex functional. You can also make it non-degenerate, having a C-infinity dependence on the gradient variable. You get a Hilder continuous coefficient, and then you get a minimizer whose set of discontinuity is of maximal dimension. A minimizer makes the energy finite, so it's automatically in W1P. So the set of no Lebesgue point cannot exceed n minus p in Hausdorff dimension. Here you get a scalar convex functional with Hilder continuous coefficients, admitting a minimizer which is nearly as bad as any other competitor. This is the condition we find. So this means that the definition of uniform ellipticity must be revisited, and must be revisited in the way we did. By the way, this is the range for the counterexample. This range implies that Q over P is larger than 1 plus alpha over n, which is a condition similar to the one implying irregular minimizers as before, but now depends also on alpha. On the other hand, we were able to prove in these papers that if this condition is not true, then you get Schauder type estimates. So the novelty here is this delicate interaction between the rate of regularity of coefficients and the gap Q over P. That depends. I don't have time to go into this, but this is a capacitor effect. This is a hidden capacitor effect. So this is telling us that already for softly non-uniformly elliptic problems, Schauder estimates are not true. And why Schauder estimates cannot be perturbative? Okay, one should say that every time I freeze the functional, so I do consider this, and this is a constant, minimizers are always regular. Always regular. This you can prove. Okay, it's just an extension of the P-Laplacian theory. So if you look at this functional, you say, this is uniformly elliptic in the classical sense. This is okay. This is Hilder. Then the gradient should be Hilder. These are okay for any choice of Q and P. Any choice. So this is not true. So this means that Schauder theory stops being a perturbation theory. So you go to the realm of perturbation into the realm of hard problems. Yes?
Here alpha could be larger than
No. Alpha is okay. Before it could. Here not. No. Alpha is between alpha and 0. 0 and 1. 0 and 1. And okay. Okay, after this paper, there was a lot of development, especially in these two papers. And essentially, now it is possible to get conditions like this, where you get functionals that are uniformly elliptic in a pointwise sense, but not in the other sense. And everything is okay. So for softly non-uniformly elliptic problems, the situation is fixed. Now we go to the real hard problems, and we want to see what happens to Schauder theory in the classical heavy non-uniformly elliptic problems. The model is simple. Take a genuinely non-uniformly elliptic problem, add a coefficient, and this stays non-uniformly elliptic. So we want to find a replacement of perturbation theory in the genuinely non-uniformly elliptic case. This is a classical topic. Now let me open a parenthesis on Schauder theory for younger people. What is Schauder theory about? Schauder theory is the effect of so-called external ingredients. You start from Poisson-Laplace equation. Nothing can be better than this. Solutions are smooth. And you want to know what is the impact of coefficients. So what can it be? Okay, this is a possible formulation in the divergence form. Then there are other formulations, but this is a model type. Okay, A is attached to the gradient. So we believe that the gradient cannot be better than A. And in fact, if A, of course, is elliptic, of course, because if it's not elliptic, then this changes the nature. So the idea is that if you make a small perturbations in the coefficients, you don't move a lot from one solution to another. And this is the content of the classical Schauder theory. Actually, this was obtained by Hopf in the interior and by Cacciopoli and Schauder up to the boundary. And there are also contributions by Giraud. And there's no other way to prove this than by perturbation, which is the classical sense. Okay, the original proofs involve heavy potential theory. Then there are modern proofs by Campanato, Trüdinger, and Simon. Campanato uses so-called Campanato spaces that were actually introduced, suggested by De Giorgi at the beginning. They provide an integral way to match the Hilder continuity. Thüringer uses convolution, Leon-Simon via blow-up, but all these methods are always perturbation. Convolution is a perturbation, freezing is a perturbation, blow-up is a perturbation. When you blow up, you're doing perturbation by contradiction. You end up with something which is linear, and then you compare with something asymptotically linear. Because on the other hand, that's the nature of the problem. You cannot do anything. And the point, okay, let's look at Campanato. So what Campanato does, you take a small ball, you freeze at a point, up to a change of variable. This is an harmonic function. So you get this reference estimate. This reference estimate tells you that this oscillation measured in an integral way. So you see, this symbol cancels the integral, and this is the oscillation. That the oscillations decay, this is actually a Lipschitz estimate of the gradient. And then you get a comparison estimate. And the effect of the coefficient is here. Then you can match and iterate. You can match and iterate. And then you can get Schauder theory by matching and iterating this. This is a classical perturbation scheme. The perturbation scheme always works because all the estimates are homogeneous. Regularity is always about iterating homogeneous quantities. If you get classical Poisson, you iterate homogeneous quantity. If you get subelliptic, you find the subelliptic balls in which the solution behaves like is homogenized. If you get Monge-Ampère, you find the sections, and it's again perturbation. If you get p-parabolic, you find the intrinsic geometry. So let's say every problem has its own geometry where it becomes a Laplacian, and then you can iterate. Okay, and the same thing you can do for the p-parabolic equation. This was done by Manfredi. This is his thesis in the 80s. And the possibility relies on the fact that when you freeze, you have Ural-Uhlenbeck theory. So the hard point is here. Okay, a side problem well known to the people in calculus of variations is the following one. What happens if you consider a functional and you have a non-differentiable perturbation? So if the dependence on V is Hilder, then you cannot derive the Euler-Lagrange equation because this quantity doesn't exist. But still you can do perturbation in this setting. So it's perturbation at a higher level using just minimality rather than being a solution. So in the uniformly elliptic setting, this is perfectly okay. And then you can carry out up to when there is a dependence on V in the uniformly elliptic case. So let me summarize the situation. Classical fact, for solutions to non-uniformly elliptic equations, this is just a model example, then C is Hilder implies that du is Hilder. For minimizers of non-differentiable functionals, then these are Hilder continuous, implies that du is Hilder continuous. All these things are using uniform ellipticity because all the estimates are homogeneous. Now, if you look at the functionals with PQ growth, for instance, they are not homogeneous by definition. And in fact, all these schemes fail even in the softly non-uniformly elliptic case. So I want to discuss these two open problems at the end. So open problem number one, this is a Schauder theory for non-uniformly elliptic, and Schauder theory for non-differentiable functionals. These are classical open problems, very classical open problems, that cannot be attacked by any perturbation argument, even in the soft case. These problems have been widely considered because if you look at the literature, everything has always been, I mean, the real difference in the literature, if you pass from uniform to non-uniform, is that in the uniformly elliptic case, you get Hilder continuous coefficients. In the non-uniformly elliptic case, you have to assume differentiability. Or otherwise, you have to assume that the gradient is already bounded, because if the gradient is bounded, you are in the uniformly elliptic regime again. So for instance, this is a problem observed by Lieberman in the review of in the review of this classical paper by Giaquinta and Giusti, where for the first time they get the nonlinear Schauder estimates in the uniformly elliptic case. He observes that, so that either you have that the gradient is bounded or you get conditions. This is also widely observed in this nice monograph that summarizes St. Petersburg School, Ladyzhenskaya and Ryaltseva and students up to the beginning of the 80s. And in fact, also Ivanov recalls that Ladyzhenskaya and Ryaltseva were able to treat presence of coefficients under differentiability assumptions and using gradient bounds, barriers, and so forth. So you have to assume this, so you go back to the uniformly elliptic regime. This is also observed, it's a theorem of Ladyzhenskaya and Ryaltseva. You see that they assume that the gradient is already bounded and coefficients are differentiable. And still, this is in the paper of Giaquinta and Giusti, where they observe that their methods do not apply in the non-uniformly elliptic case. The battery is down. Yeah, the battery is down. Okay, but I will probably we can use this. Okay, it's okay again. Right. Okay, so it's so this is the situation. So the problem is being widely discussed. Okay, solutions are in a paper by Cristiana De Filippis from Parma and myself, and we catch both the problems. And the crucial point is, of course,
they are recording and then.
Okay, right. Okay, so the solutions are in these two papers by Cristiana De Filippis from Parma, and we catch both the problems. And the crucial point is to get L-infinity bounds. After you get L-infinity bounds, then you can, with some efforts, readapt the more classical methods. But still, in that case, you need some work. But the real hard point is easier. So the first result is about non-differentiable functionals, the model considered by Giaquinta and Giusti many years ago and then by other people. Then we get PQ on the eigenvalues. This is Hilder, and then we have this dependence. This is a positive universal constant, and you see that this alpha over n reappears. So alpha over n appeared for the first time in the double phase case, and here we have the same condition. So there's a universal interplay between Hilder continuity and dimensions, and this is due to a capacitor effect. I mentioned this before, but there's no real time to discuss this. And we also have a result about intermediate dependence when there is interaction between V and dV. And this is a more delicate bound, but this is more technical. Because here we escape the range of Schauder theory, because Schauder is just dependence on X and not on V, but we are also able to say something on V. And this is about non-differentiable functionals. Now we go to the real Schauder theory. So we take a non-uniformly elliptic operator, we add a coefficient, and again we have this kind of situation. Here we have a square that worsens the bound, but alpha over n is always there, because this is a universal object, as a universal scheme. And there's no perturbation method working at this stage, 0. For those who are interested tomorrow I'm going to talk about more details about this. And okay, here the functional can be degenerate, and you get that U is locally Hilder continuous. You cannot get better than this already in the P Laplacian case because of counterexamples by Ryaltseva school. But when the situation is non-degenerate, this and this, so the problem only occurs at infinity, so purely non-uniformly elliptic but non-degenerate, then you can recover the full Schauder theory. So this is Hopf-Kachoplian-Schauder reloaded. That's why I called it. So this is the full non-uniformly elliptic Schauder theory. Huh? Before was some exponent, because I mean, if you get a minimizer already of this functional,
not C alpha.
it cannot be, because this is degenerate. So if you already take this simple functional, then the gradient is C0 alpha for some small alpha. Okay, no, it is conjectured to be 1/3. Though the limit, to be bounded from below by 1/3. But it cannot be the same by counterexamples, because it's degenerate. So this has nothing to do with non-uniform ellipticity or coefficients. Here you get exactly the same thing. If you add that the functional is non-degenerate, then you get the same exponent. Of course, you can consider also the case of V, but here you have to assume that P is larger than N, and we get the same result. And let me skip about this. Okay, let me talk about equations at the end, because this is for minimizers, which is the more natural setting for non-uniformly elliptic problems. Okay, in the case of equations, there is an ambiguity on the notion of solution, always. A minimizer of this guy is automatically in W1P, by definition. If you just consider this equation, to give sense to this equation, you don't need that the gradient is W1P. It just can be in LP minus 1. So these are called very weak solutions. Okay, someone calls them very weak solutions. And of course, in the case of PQ growth conditions, there's an ambiguity. So energy solutions are replaced by this condition. So they automatically have to be in the best possible space. Is this really necessary? So can we deal with very weak solutions in the PQ case? This recent result by Colombo and Tione suggests not, and this proves a conjecture by Ivanez and Sbordone, because if you take an equation like this and you take P, which is then you can prove that there exist solutions. If you start by a solution which is close to BW1P, then very weak solutions are not energy solutions. This proves a safe conjecture by Ivanez and Sbordone. Ivanez and Sbordone conjectured that this was safe, and one should always be careful when things are safe. I mean, actually, I don't know why they conjecture this, because in regularity theory, as soon as you escape the energy solutions, then all bad things might happen. But still, this is not true. So, in the classical literature, there are two approaches. Either you start with W1Q solutions, or you prove existence and regularity simultaneously. Because the difference with minimality is that minimality and convexity always pick the right objects, while solutions can be more general. So we use the second approach, which is classical in the literature. So we consider a Dirichlet problem, which is non-uniformly elliptic, and we prove that you can solve the problem with Schauder estimates. And so these are Schauder estimates for every non-uniformly elliptic equation. So this puts a dot on this very long-standing question of proving Schauder theory. So how do we prove this? More details are going to be given tomorrow. And the proof combines a lot of several ingredients never used in the non-uniformly elliptic setting. So we use nonlinear potential theory via version of certain nonlinear potentials introduced by Having and Mazia and used by Hedberg and Wolf. And then we use fractional Kachopoly type inequality with a fractional variation of Bernstein method. That was for the first time, okay, we will see tomorrow, used many years ago in a paper of mine where so what we do to prove that the gradient is bounded, you usually use something called Bernstein method that tells that if you have an harmonic, in the simplest form is if you have an harmonic function, then a certain convex function of the modulus of the gradient is a subsolution of anything. So you cannot use that this is a subsolution because this involves a differentiation of the problem while the problem is non-differentiable. So we read the Hilbert continuity as fractional differentiability. We write down a certain Cacciopoli typing equality on level sets for the fractional derivatives of certain special combination of the modulus of the gradient, and then we start making iterations out of that. But the point is that in order to write this fractional Cacciopoli typing equality, you have to go to a sort of localized version of Littlewood-Paley theory, where you replace the decomposition of Biesov functions via atoms that are close to harmonic functions with atoms that are solutions to nonlinear equations. But this is very, very delicate. It's a long proof. It takes something like 50 pages. But at the end, you can overcome all these facts, giving a direct proof that the gradient is bounded, also if the problem is non-differentiable. And I think that we can stop here, and thanks for your attention.
Is there any question or comment? Okay, so let me ask something about what about this fractional? Does this fractional tool that you were describing just comes from the work? Where does it come from?
No.
Does it come from your work on non-local equation? On non-local? No.
This is a purely no. This is the idea. No. This is. No, doesn't come from no local equations. This actually I started developing more than 20 years ago. And okay, there are many people working on non-local problems, including you. But the problem here was to use fractional techniques in local problems. So the idea is that you... we need an eraser. So the idea is roughly the following. You get an equation of this type. And you want to prove that a certain quantity, let's call E of the U, is a okay, when there is no x, right? And for instance, you have the P-Laplacian equation, you get that E of the U, like du to the P, is a subsolution. It's a computation. It's also essentially this is Uhlenbeck's trick in the vectorial case, and for p equal to 2, it's Bernstein. Okay, if you have an equation here with possibly a right-hand side, for instance, you have two obstructions. First, the right-hand side destroys the subsolution idea, because you have a right-hand side, you have no control on the right-hand side, and most importantly, you cannot differentiate with respect to x if this is Hilbert continuous, because this goes by differentiation. Okay, so the first idea is that if you don't, how do you prove that the gradient is bound, that a subsolution is bounded? You run Moser's iteration or de Giorgi's iteration. So you skip the Giorgi's iteration, you don't skip this fact, you skip the fact that it's a subsolution, you go directly to the Cacciopoli inequality. So the Cacciopoli, and then you prove, then you have, in the classical sense, a Cacciopoli inequality of this type. Let's say, depending on this is the level set. So if you have a derivative here, you have to put this. This is rho square. This is b rho. This is du minus k plus p. Plus terms. You see this term, square. You see, these terms prevent you from getting a subsolution, but you can still iterate this. Okay, now this is if the problem is differentiable because you get a second derivatives. If the problem is non-differentiable, what can you do here? If the problem is non-differentiable, you prove here, here. What does this mean? This means Gallardo norm, of course. Okay, how do you prove this? This is very, very heavy construction because essentially what you do, you mimic the construction of the dyadic decomposition of the Biesov spaces. You prove this in Biesov, actually in the Biesov spaces, in Nikolsky spaces. You make a dyadic decomposition on the size of the ratio of the size of the difference quotient that you are using, and on each place you use an atom which solves which is a solution to a frozen problem. Then you have a dyadic covering that mimics the Biesov space, and then you get this. You get this. Now, after you get this, you know that the Giorgi's iteration is only based on geometric iterations. So any improvement in the geometric setting leads you to what you need to have. So here you use fractional embedding, and then you can write down that the gradient is bounded. Of course, to write down this is a major pain, of course, because there will be other terms here. So this is okay. This is how to handle the general geometric iteration mechanism, and then you have to handle these objects that incorporate the information on non-uniform ellipticity. Of course, there is something I didn't tell here, that the equations that the inequality you will have cannot be this one because this is homogeneous. So what you will have a certain quantity here in something which that contains the L infinity norm of the gradient in something that we call the renormalized fractional Caccioppoli inequality. And a magic fact here happens that okay, will be described tomorrow. Okay, well, will be described tomorrow.
Thank you. Yeah, it's technical enough. Yeah. Any other question or comment? If not, let's thank the three speakers of the day. See? And thanks for coming to everybody. Thanks.